who are not familiar with crypto understand that, if your randomness is not proper, your crypto likely won't be secure. And the normal random numbers which Linux RNG provides is usually good, but it's, again, I don't have time to go into details, but it's basically kind of collects the entropy for, seeding the random number generator from various sources, and it kind of works on the normal scenario, even in legacy VMs. But the problem that in confidential computing, the sources suddenly becomes observable by the, what we consider, attacker, by the entity outside of TCP. So it's primary things like, interrupt timings, timing information, and so on. And again, like being maybe not an encrypted person, you can understand, okay, if your all entropy sources for your random number generator is observable, maybe you don't have a good randomness. So we wanted to fix it, so we started this discussion, and at the end, there was a lot of also things about, and one thing I didn't mention is that we do have one source which is outside of host control, which is on x86 platforms, is RD-run, RD-seed instructions. They're basically gonna give you random numbers outside of the platform embedded DRNG. And that is the one which is like host has no control over. So we try to find a way, what's the correct way to essentially making sure we're getting that randomness in confidential computing setting. And if for some reason we're not getting it, we actually don't boot, because this is really dangerous to boot with randomness, which is not good, and start proceeding with the crypto. So we had a long discussion. At the end, there was an agreement, and Jason, who is the maintainer of RNG, submitted a patch, and I think it's merged by now. And the last thing I wanted to talk about shortly, kind of, again, the thing which I have talked about, but it still kind of remains unsolved problem, and we're still kind of trying to figure out what's the correct way of solving it in Linux. So we talked about that, we need to minimize attack surface. Attack surface is way too big. And the biggest attack surface is still, in our understanding, is in drivers. And we have way too many drivers enabled in a typical distribution. And they're definitely not needed. In confidential computing setting, most of them, there are way too many to do any hardening, auditing, fuzzing, whatever kind of things we can do. And even if the device is never needed inside of a confidential computing guest, the host can pretend any device to exist, because the PCI bus, at least in typical, if devices are allowed to be controlled by the host in confidential computing setting, the host can pretend any device to be visible on a bus. And Burber's solution, let's disable all the drivers and harden the enabled ones. That's actually the hardening of enabled ones is actually going pretty well. As I said, Virtual subsystem, VM bus, some other drivers, they actually they work on it, and the drivers have been hardened. But we still have this problem that we have way too much thing hanging there which hasn't been disabled. And this brings us, okay, we need to disable it, and of course we know how to disable drivers. We have a number of mechanisms in kernel to do this. The kconfig is the best choice, the modprop, which is somewhat a subset of it. But the problem with the first two is that all of it essentially requires to creating a custom distro. And we have the distro, we have big companies who are doing the distro, who are providing distros, which in theory they would have resources to do it, but it's very, it doesn't scale well. And then also, if you think of other players, maybe smaller players, who want to have a custom, want to have their own custom kernels run, they definitely won't have time to, take, let's say, a certain typical distro and go play with this kconfig things and stuff to get it to, reasonable working and functional state, and also disable all the, default drivers which are built in for some legacy reasons. So it's actually not the ideal approach, and the kernel developers might be able to say that, yeah, there is a mechanism, just use this mechanism and we are done. But in practice, the security people know that when mechanism is not scaling, when it's not good, like for actual usages, practical usages, it's not going to get used, and we're back to the problem. There is another approach that you can just forget about all the ICPI, PCI, and just use a device tree, pass a minimal configuration, and I guess from security point of view it would be the best. But the problem is that there's way too much things in the existing infrastructure which actually relies on PCI and ICPI being present, and deployments are used to have these things kind of embedded in the stack. So we might have some deployments with a device tree, but in practice we also need to find a way to make it secure with the proper full stack ICPI PCI stack. There is another direction in this work, and this is what we are kind of closely looking into now, is that there is what we call trusted I/O direction. So there is in confidential computing, there would be a way that physical devices will start to support sometime in the future. Again, don't have time to explain in details, but it's basically a way to securely connect this device into your confidential VM, establish a secure channel, MMIO, DMA, everything is going to be done straight into the private memory of a confidential guest. And you can also have secure mailbox exchange over SPDM protocol and things like that. So you will have a way to establish a secure channel. So first establish trust in the device you're connecting to your VM, and take the host and hold the host software outside of the picture. And while this solves a problem for these devices which will support this stack, it definitely doesn't solve a generic problem of getting rid of all the other devices and device drivers we don't need. So, I mean, if we have a way to say, okay, I want to run my confidential VM, and I'm only trusting these trusted I/O devices which connect to me with this, this set of measurements and these certificates, that's good. But we don't have this mechanism today, but we are looking actually into the how we can kind of share the touch points in the code with the basically trusted I/O work. The fact how we solved it in the past for the for that proof of concept is that we had basically a runtime filter, which device runtime filter, which we call it, which would be kind of configured through, in our case, this latest iteration was through just a binary ICPI table where you can put what devices, this guest should expect to find on the PCI bus, any other devices won't be enabled. And you can actually, using this configuration, you can do more than just, enable, disable things like, modprobe or kconfig. And this was something which was also suggested when we talked back last autumn with virtual maintainers. We're saying that, but you can make it more advanced. You can add policing things here. For some device, like virtual devices, they operate in different modes, and you might have different kind of, let's say, trust levels in these different modes, and you might not want to enable only a subset, which, let's say, you harden too fast, you have more confidence in. Or you can do different things, like we're also now looking into this situation where we can actually have these devices provided in the different levels. So we can have them provided, let's say we can have a device basically in the control, being under control of the host, let's say some networking device. And because we are using end-to-end networking security, it's okay for that device to be under control of host, and its MMIO could be shared, in the open shared memory between the host and the guest. But when we could have the same device maybe hosted inside, and Carlos is going to talk about when we got to this concept of SVSM, we can have the same device hosted inside the TD in a different privilege level, or inside of this confidential guest in a different privilege level. In that case, that MMIO should be actually in the private memory of that confidential computing guest. So you can also pass this kind of information saying, okay, here is the device you should be expecting, and this is the configuration, secure configuration for this device. So as I said, this is still work in progress, and we are looking kind of to see if we can share the only code touch points with the trusted I/O work. Okay, so go over to Carlos.
Okay, so we're going to cover SVSM. There is a presentation by Jörg later today. He's going to explain in much more detail, but I'm just going to talk about it a little bit from a threat model point of view. The idea of the secure VM service module is that it provides an isolated environment in which to take care of the operations that have to do with confidential computing, like validating a page, things like that. So with AMD Secure Nested Paging, which is the latest version of AMD memory encryption technologies, we introduced this notion of, that Elena was mentioning, of the VM privilege levels. So the idea is that if a guest is running in VMPL 0, then that guest is going to be able to execute this sort of operations, but otherwise VMPL 1, 2, 3 is not going to be able to do it. So we do this so that we can offload this type of operations into the SVSM. So yeah, SVSM runs in VMPL 0, and it takes care of this sort of operations that require higher privilege levels.
maybe one thing to add here, so you can think of this SVSM for people who are kind of not familiar with this concept is that, so previously we were talking that there's a host and there's this confidential computing guest. Now inside that we partition or divide this confidential computing guest inside into some trust levels or partitions depending on the terminology differs between company, but you can have actually more privileged levels inside the guest and less privileged levels. And the less privileged levels could be actually used to run this, let's say your Linux kernel and your operating system, your workload, and more privileged level now becomes, which is what we call this guest security manager. So this is like, the mini kind of hypervisor kind of mini layer, which can start providing things like services and other, it can give more security benefits. Because again, from the threat model point of view, if previously we run without the security manager, we are, and if we put a default, let's say Linux kernel, it's exposed. But now we are starting to look, okay, can we actually make situation better with utilizing this security manager as a thin layer, which is like trusted because it runs inside this confidential computing guest to provide additional protections.
Right, so to be clear, in the case of the SVSM, you first launched the SVSM at BNPL 0, the SVSM will validate the memory, things like that, and then it will launch the guest kernel at BNPL 1 or higher. So how do things change from a threat model point of view in the case of SVSM? Some of these things are theoretical, they're not necessarily implemented, but these things we could potentially do. In terms of PCI discovery, the host can pretend that there is a device that doesn't exist. So the idea is that the SVSM could emulate the PCI configuration space. So the registers with vendor ID, those sort of things, including TD-ISP devices, by the way. The CPU has to communicate with a device, either with for legacy with programmed I/O or with memory mapped I/O, but that's hypercalls. So you are taking untrusted inputs. And the idea is that the security manager could intercept this kind of PIO, MMIO request and allow only a limited set and then sanitize the rest. Same thing with shared memory, DMA. The guest kernel actually shares all the I/O remap regions, which is not only device driver mappings, but also core kernel mappings. And with using these PCI discovery limitations, you can make it so that the core kernel mappings remain private, even if you use I/O remap. And this will only explicitly allow shared mappings for the devices in the host. Interrupts are a big thing too. They're under control of the host. In the case of TDX, as Elena mentioned, anything below 31 is not even accepted. And in the case of SMP, we have restricted injection, which only allows pound-HB. So pound-HB, it's a doorbell, and then once you get there, the handler can decide whether or not to allow the interruption. We also have this thing called alternate injection, which relies on BNPLs. So the problem basically with restricted injection is that you need an enlightened guest. You need a guest that understands pound-HB and doesn't allow anything else, and that's not necessarily always the case. So the idea of alternate injection is that you have a guest or SVSM running on BNPL 0, which can receive any type of interruptions, and then that BNPL 0 can forward to other BCPUs, whatever it decides to forward. So it's important to note that these things by themselves are not mitigations. They don't provide any sort of filtering. They're just mechanisms by which we could potentially prevent attacks. So we could restrict and verify the range of exceptions related with the Ahoy attacks as well. Timers, obviously controlled by the host. So as Elena was mentioning, it's quite interesting, the going back in time thing, the virtual guest DSC. And the idea is that SVSM could potentially provide a secure TSC or mechanisms to retrieve real-time information. And in the case of SMP, AMD in particular doesn't have anything to stop the scheduler from messing, but as we mentioned, denial of service is not really a guarantee. ACPI tables have to be attested. SVSM could, and in fact has a BTPM. But this is not a perfect, it's a little tricky because there are some tables like the DSDT that are quite large. So, and also you need to allow a limited set of them to go through. So before we go to questions, I would just like to wrap up with a quick thought. Confidential computing Linux is not the only operating system trying to support confidential computing. I know Apple is investing in hardware and in software. Microsoft, Android, I'm sure everyone is. And we, the Linux kernel community, we don't want to be left behind, but we need to be cognizant that we face unique challenges due to the monolithic nature of the kernel, our reliance on interruptions, and that sort of thing. And I think that's everything from our side. If you have any questions.
Yeah, and just to advertise, like this very cute logo is all credits to Carlos. So this is like, we pinging with a coconut. The cocoa is a confidential term for confidential computing. And we actually have the stickers over there. So if you want to grab the cute sticker, you're welcome. Any questions?
Do we need to give them this?
Oh.
If you ask me the question, I can repeat it out loud.
Okay, yes. The device filter is more code discussed. It makes sense to me to have more attested builds that you can have as part of your attested, your attestation policy. There's another researcher at Intel, Marcella, but there is the intro to attestation format for builds. Build configuration as part of the attestation, where you could include the kconfig, et cetera, and your policy can check for if you've disabled particular drivers. This just involves distributions figuring out a common way to present their build attestations in their packaging. And this is something that I'd really like to have a conversation about.
Yeah, we should definitely talk. I think we kind of...
So the question is that as opposed to device filtering, attestation may have other benefits. She's mentioning a work in which they are generating an attestation report of a configuration for when you load the kernel and the entire kconfig, and they want to have a discussion about it.
Yes, so I think kind of everything needs to be, the desire is to attest to the configuration. So whenever it's build time configuration or runtime, I think this is where usually like all the pitchforks are about, because, can everyone be really truly okay with build time configuration? Because typical distro still leaves a lot of things enabled into the kconfig.
I would also add that in the case of the Ahoy attacks, attestation, you can attest, for example, the kernel image, but the way they were figuring out which pages to attack was because they modified an early boot image that itself then boots the kernel and takes care of kernel address, layer randomization, that sort of stuff. So attestation can only go so far sometimes.
Anyway, but I think we need to talk about it. So I think the general kind of desire of having a way to attest the configuration is just a question of how big is this. I mean, we can attest to anything. I mean, the way like how we currently kind of thinking of providing it for ICPI, we do measure ICPI tables, so they can be attested. So that's, but if we can, agree on a common format for which would cover, trusted IO devices as well and everything, so that might be a way to go. I agree.
Thank you.
Thanks. One of the recurring problems that concerns people have is around UEFI injection from from CSPs, just putting it into your VM, right? Can the SVSM mitigate some of the problems that may arise from that? Because you just can't be sure at the moment what's going on.
So which exactly injections, just to make sure I understand?
So when you go to Azure or to Google or whatever, and you ask for a confidential VM, if that's what we're going to call it, typically it comes with the UEFI
Oh, you're saying
from
virtual firmware is actually belonging to the, the CSP who's this.
exactly, yeah. So can you be mitigating against some of the concerns around that?
Yeah, so I think it's the same kind of thing as that, you have to establish trust in this firmware, and there are means of doing it. So, you can publish this, there's one of the typical firmwares being used is CDK2, which is open source, and, very specific configuration for confidential computing. And if the CSP providers who is going to be doing particular build of this, if they provide the actual, the reproducible build which you can compare, because if the firmware is attested as well.
Yeah, so I mean, good luck with that. I think the question really was whether SVSM can be used to mitigate against some of the bad things that could happen there, because I just don't believe at the moment that we're going to see those sorts of changes from the
and by
CSPs.
Bad things, you mean, let's say CSPs, embedding into the firmware some, vulnerable paths or.
Yeah, exactly.
The BTPM.
Well, the whole thing we want to do is to take the CSPs out of the trust model, right? So
probably a good discussion for George's presentation on SVSM, but the BTPM can attest the OBMF.
But I think the question was, we know how to attest the virtual firmware. The question is how to make this attestation real in practice, that the tenants who are, getting this VM can actually say what this virtual firmware really is. How do you build backwards?
Well, the question was, I'm assuming that's never going to happen. Is there anything we can do about it?
But it is happening, because the BTPM.
Well, it's slow and it's going to be difficult to manage. So I get that it is happening, but can we use SVSM to help us in the meantime?
The problem is that everything, when you start if you started virtual firmware running inside of your TCB, and you don't have a way to establish trust in this integrity of this and trustworthiness of this code, what can we do from inside of that same TCB? Apart, we can go into, it's kind of a bit of chicken and egg problem. So you have to have some way to establish a trust. And I think it's more like the pressure would be, I think the pressure at the end would be on CSPs to do this, because, at some point people will understand that, there is this bulk of firmware they're running, which they have no maybe understanding of what it's doing. It's in their TCB, and there would be pressure to make a reproducible builds and things. But I don't know how to, I don't think any software, it's the first software which runs. So, if that is compromised and there's no way to establish trust, nothing which runs later could, recover from that situation.
Let's discuss.
Yeah.
I'm doing that for Google. We're going to have a transparent build of the firmware.
Thank you.
So somebody is doing this already.
It's happening. It's good.
Any other questions? Okay, if not, thank you everyone for listening.
I'm going to put a mic over here on this table and a mic over there on that table. So if you want to, if you have questions after a talk, you can come up to either one of those. You just have to slide the button over and then it's live.
Got it.
Yeah, now it's on. Yeah. All right, let's get started. Welcome to my talk about securing confidential VMs with Coconut SVSM. My name is Jörg Rödel, I work for SUSE, and I'm the maintainer of the Coconut SVSM project. So Coconut SVSM was mentioned in the previous talk already. I want to go into a few more details in my presentation. But first of all, what is my agenda? So I will start with an introduction of the project. Then I dive a little bit into the Coco VM threat model. That also was part of the previous talk already. I will add some different perspective to that. Then I show you how the threats are usually mitigated using a hardware extension. And then I get to the Coconut SVSM and explain how the Coconut SVSM helps to mitigate things that cannot be mitigated in hardware or not easily mitigated in hardware. And I will finalize the talk with the project status, so where we currently are with Coconut SVSM and what are our future plans. So let's dive right in. What is Coconut SVSM? That's a question I get from time to time, and this is my default answer. So the Coconut Secure VM Service Module is a platform to provide secure hypervisor services to confidential virtual machines. So that's a very generic sentence. So what does it mean? That's the topic of my talk. But first of all, some history of the project. So I started with it in early 2022, with starting some code to prototype a few things. Over time, it grew and came to the point where it could execute or where it can run a Linux guest OS in a confidential VM in early 2023, which was the point where I decided to publish the project, to make it open source. This happened at the OC3 conference, the Open Confidential Compute conference last year. And this was, I think, quite successful. Since then, we gained a really good developer community. So up to date, we have 23 contributors. We made good progress. Since the project was published, we got file system support in the SVSM. We have support for tasks, so we can run different tasks and switch between them. We gained a TPM emulation recently, and the project also gained a lot of continuous integration features and fuzzers to test parts of the code and make it and check whether it's still secure and bug-free and catch bugs early in development. Another important point I want to highlight here is that the Coconut SVSM project applied to become a project of the Confidential Computing Consortium. This happened in November last year, where I presented the project to the Technical Advisory Council, and in December, the Technical Advisory Council accepted the project. And then the onboarding is in progress, which takes some time because some legal stuff is involved. But I'm happy to announce that onboarding is mostly finished, so the project will soon be part of the Confidential Computing Consortium, which is, I think, really great. So let's dive in. Let me present you a little different perspective, or another perspective to the confidential computing VM threat model. So if you look at the normal virtual machine setup, you have a virtual machine which runs your kernel and your applications, and you have the hypervisor which basically drives all of your virtual machine and does certain things to actually make your virtual machine running. The most important things that the hypervisor does, or the most important tasks of the hypervisor, are memory management, so managing the memory the virtual machine can use, handling intercept of the virtual machine, inject interrupts, and emulate devices. So now what happens if you don't trust the hypervisor anymore because you don't own the hypervisor and you still want your data to be secure? This is not really possible when the hypervisor does all of these tasks. And now let's look into how mitigate these possible attack vectors from the hypervisor to the virtual machine. Usually there are two options to mitigate the attacks from the hypervisor. There is mitigation with hardware extensions, which is what confidential computing is all about. Or if that is not possible because the extension does not provide or does not include all features to mitigate all attack vectors, then there's still the option to move hypervisor tasks into the guest context. Most mitigations available today use actually a mix of both options. So even the hardware mitigations need guest support code or support in the guest kernel or in the, to make use of that. So how does threat mitigation in hardware works? So there are hardware extensions. Those were also mentioned in the previous talk already. Every hardware vendor comes up with a different one. So we have on AMD SVSM, on Intel we have TDX. ARM is coming up with the confidential computing architecture, ARM CCA. And RISC-V is also specifying an extension, the confidential virtualization extension. These extensions have a mostly identical feature set, so feature-wise they are not very different. The implementations actually differ. And one important thing to notice here is that the non-x86 architecture extensions are closer to Intel TDX than AMD SVSM in the overall architecture and in how they have to be used from the hypervisor. So in my presentation, I will focus mostly on the x86 architecture extensions. I will note differences between AMD and Intel when it is important, but all concepts I'm talking about here are also applicable to non-x86 architectures. So let's look how the hardware helps us to secure hypervisor functionality. So first is memory management. Without confidential computing, the hypervisor can read all guest memory. Now there are hardware extensions, and every confidential computing extension supports that. The first protection is basically encrypting guest memory, so that only when the virtual machine is running, the memory can be seen unencrypted. And the hypervisor can only see the encrypted state or no memory at all. But this is only part of the protection that is needed. There's also a mitigation against attacks against the encrypted memory, which are mostly memory remapping and replay attacks. So even with encrypted memory, the hypervisor could replay old state on encrypted memory, or it can map data from one guest physical address to another. This is also mitigated by hardware, not in that it is prevented, but such behavior is made detectable in the virtual machine, so the virtual machine can detect when the hypervisor is trying to attack the virtual machine using remapping or replay attacks. And with that, memory management can be considered secure, so the data is stored in the secure way. How is intercept handling secured? So for intercept handling, the hypervisor needs usually access to the guest register state, which is problematic because the register state can contain secrets, like AES keys in floating point registers. And the register state can also be used if it can be modified to attack the instruction flow by changing stack pointers or instruction pointers of the guest. So to mitigate the attack vectors from intercept handling, the hypervisor cannot do the intercept handling itself anymore. So this is also mitigated by hardware extensions or in confidential computing by basically not trapping intercepts to the host hypervisor, but trapping them to an exception in the guest kernel, and the guest kernel can do intercept handling itself. On AMD, this is the VC exception. On Intel, this is the VE exception. So intercepts are handled in the trusted guest context this way. The trusted guest context has access to all registers. And there's usually also a para-virtual interface to the hypervisor to actually get data which is needed to fulfill the request. For example, MSR reads and writes. The guest cannot emulate it fully on its own. For that, to get host emulated MSR values, the guest has still to ask the host. But this happens via a para-virtualized protocol. And with that, intercept handling is basically removed from the hypervisor and happening in the guest kernel now, and this way it is also made secure. The next thing is interrupt injection. This is where it's a difference between Intel and AMD. I think this was also briefly mentioned in the talk before. So on Intel TDX, the architecture provides a virtualized interrupt controller, a hardware virtualized interrupt controller for the guest, which actually prevents some kinds of IRQ attacks. It basically prevents that the interrupt can be injected at any time, even when the guest is not expecting it. It does not allow to limit the number of vectors that can be injected, but the guest kernel does not need to be prepared to receive any interrupt at any given time, even when interrupts are disabled. So this is mitigated via a hardware feature on Intel TDX. On AMD, it's a bit different because there is no hardware virtualized interrupt controller for confidential VMs. So the feature here is restricted injection, basically limit the injection of events to an HV vector to one exception vector. The guest kernel has to be prepared to receive this HV vector at any given time, at every instruction boundary. But this is something that can be taken care of in software. The issue here is that it's not only done with injection, but there's also the point of interrupt delivery. And the interrupt delivery has to happen inside guest kernel now. So all the interrupt delivery logic that's usually lived in the hypervisor is now moved to the guest context. So the guest kernel has to decide itself when it is ready to deliver an interrupt. This has some challenges and is a complex thing to do, so, but with this way we can make interrupt injection secure on AMD. The last point here is device emulations, and this was broadly covered in the last talk. This is not so easy to mitigate because there are only limited hardware extensions to allow to have device emulations in the guest side. So this is not so easy to mitigate. So what options do we have? We can harden Linux device drivers. This was what Elena and Carlos were talking about. This is an important effort. What alternatives do we have? We can emulate devices in VE VC handlers. That is possible because VE and VC handlers get all MMIO accesses or MMIO traps into these handlers, so these can be used to actually emulate devices. Problem is, we still need a simpler interface to the hypervisor to actually get the data from the devices, so for a disk or network device, for example. So this is a rather questionable exercise. And the most problematic thing are actually devices that carry security-sensitive state, because those devices cannot be emulated by the hypervisor when the hypervisor is untrusted. Even when the Linux device driver is hardened and secure against any attacks from the device, still the state of the device lives in the host, which is untrusted. So this cannot be secure in a confidential computing environment. And also, the security capabilities of those devices usually live on the fact that the guest OS also cannot access the device state. So we need a way to protect device of security-sensitive state of security-sensitive devices from the guest OS and from the hypervisor. Example devices are TPM device, but also an EFI variable store, for example. And this is where Coconut SVSM comes into the picture. So Coconut SVSM is an additional software component that runs within the confidential virtual machine, and which aims to provide these services like emulation of secure devices to the guest operating system. Coconut SVSM relies on a hardware feature of confidential virtualization extensions, which is memory isolation within the virtual machine. So newer hardware generations support memory isolation within confidential virtual machines. On AMD SVSM, these are VM privilege levels. On Intel TDX, it's partitioning. Others will probably follow. And what all of these extensions have in common is that they provide, that they establish a privilege model orthogonal to the CPU privilege levels inside the virtual machine. So on AMD SVSM, for example, you have 4 VMPLs, and in each VMPL you have all 4 CPU privilege levels from ring 0 to up to ring 3, and can execute code there on any CPU privilege level. On every of these architectures, there is a most privilege level, which is VMPL 0 on AMD and L1 on TDX, which has more privileges than the others. And the key feature of these features is that the highest privilege level can basically define which parts of the guest memory the lower levels can actually access. And this can be used by software like Coconut SVSM that runs in the highest privilege level to actually define memory which is not accessible to the operating system and which can be used to store state of security-sensitive devices. And this brings us to Coconut SVSM, which is a software that is designed to run on the highest privilege level and help OSs running on lower privilege levels in confidential VMs. So a bit of a dive into the project. Coconut SVSM is an OS-level software designed to run in confidential virtual machines, currently only on AMD, but I hope this will change soon. It is written in stable Rust. It implements common kernel concepts, it has memory management, it has a file system. only an in-memory file system, but it has a file system. It has a task concept. It uses cooperative scheduling, which is mostly due to the fact that there is up-to-date no interrupt source that would allow preemptive scheduling. The code base puts a strong focus on isolation. This is not completely ready yet, but we are getting there. And the most important feature in my mind is that Coconut SVSM wants to run the services it provides to the guest operating system in user mode. So have further isolation there and isolate the services that run with regard to each other. The project is on GitHub. Under the URL, there's a whole project around it, which does not only contain the SVSM repository, but also support code for Linux kernel, QEMU, and EDK2. These, except for EDK2, no, not even EDK2, but all of these projects do not yet have upstream support for running an SVSM, though, so we still maintain these changes in support repositories in our Coconut SVSM GitHub project. Coconut wants to support multiple hypervisors, so not only KVM. It is currently mainly developed on the KVM hypervisor with a prototype support code. Hyper-V support is currently emerging, and possibly other vendors are working on support for using SVSM on their hypervisor too. So that's a defined goal of the project, to support multiple hypervisors. And one way we do that is by using a standardized boot protocol, using the independent guest virtual machine, or IGVM file format. Not sure if you have heard of that already. That is a file format defined by Microsoft, which basically allows to describe the initial memory layout of a confidential virtual machine. Which means that when you have such a file and a guest platform configuration, you can calculate the expected launch measurement from only that file and compare that to the actual launch measurement of your VM later and see if it's identical. And if it's identical, you know that the IGVM file was loaded correctly by the hypervisor, by your untrusted hypervisor. But not only that, the IGVM file format also standardizes parts of the hypervisor interface, which is great. For example, getting the memory map which the SVSM needs, or some ACPI tables. Which is also a good feature of IGVM, because otherwise we would have to have interfaces to each hypervisor we want to support for getting this information. The QEMU, which we host on the Coconut SVSM project, already has support for IGVM, and we use it as our standard boot protocol during development right now. So the code is there. We are doing work to push it upstream, but yeah, we are getting there. Hardware support, what hardware do we support? As I said, we currently develop on AMD SVSMP, where it relies on the VM privilege levels features. There is support for TDX emerging 1.5, because 1.5 is the version that adds TDX partitioning support. There's a prototype branch for that available on GitHub. And there's even support for non-x86 architectures is currently the planning phase. This requires some bigger reworks of some code parts, because we need the right abstractions in place to actually add code like page table management and everything for other architectures. Also boot up code and CPU setup code and stuff. User mode, I mentioned that already. It's one of the key features the Coconut SVSM project wants to support. So services will run as tasks in user mode, because tasks have less privileges, of course. So if there's a bug in one service, you do not usually get to get secrets from other services. So there's isolation there. And we also plan to have a security layer, which limits what services can do and how they can interact with the SVSM kernel. You can think of it in the terms of an SE Linux thing, but just simpler and for the SVSM and its syscore interface that is emerging. So here's a high-level design as a summary for the Coconut SVSM. So the Coconut SVSM runs alongside the guest OS within the trusted execution environment. It makes a distinction between kernel mode and user mode. The kernel mode runs the Coconut kernel, and the user mode runs the services as separate tasks. And the guest OS runs in the lower VM privilege level or in another TDX partition and interacts with the SVSM either directly or indirectly. And the guest OS, of course, has a separate kernel user mode differentiation. So putting this all together, with this design, we can actually have add device emulations to the guest context. We can move them out of the hypervisor into the guest context. And starting with devices that cannot live in the hypervisor, like TPM and an EFI variable store, the Coconut SVSM allows to emulate them actually inside the guest context. Other device emulations still live in the hypervisor and are untrusted, but this is where device driver hardening comes into the picture again. So, what is the status of the project and what are our plans for the future? As I said, it runs on AMD SVSMP systems. We have essential kernel functionality implemented. We can handle SVSM core protocol requests on the AMD platform. We recently merged a TPM emulation with no persistence yet, but still it's a start. It still runs in kernel mode because user mode is not fully ready yet. It's emerging. We are getting there. We have support for kernel tasks, and as I said, user mode support is emerging. Speaking of user mode, where are we? As I said, this is one of the key features, so I want to highlight it here. So there's currently a PR pending, which adds code to load ELF binaries and execute them in ring 3. So this is, there's code for that now with only 2 testing syscalls, which are not very useful, but it's a start. I started the work on a Rust user space library, which contains of a syscall wrapper crate, a heap allocator for user space, a custom linker script for binaries that are linked and targeted to run in user mode. So that's where we are. What are the next steps? The next steps are to first build an init task that launches the other services or that reads some configuration and then launches other services. That, of course, requires syscalls, getting the user mode support library to a certain point. And when that is up and running, the plan is to move the request loop into a separate user mode task and then move the TPM code into another user mode task to have all of them isolated against each other. So this is the roadmap, which I hope to achieve within the next couple of months. What else are we planning to do? Another important thing is persistence. This is also being worked on right now in the community because support for persistent state is actually needed because it makes sense to persist actual TPM state. For example, you can use the TPM to store the key of your disk image, so and you can't regenerate the key every time you boot up your VM. So it makes sense to persist the TPM state, and when your VM boots up and all your measurements are correct, you get the disk key from the TPM. So this is one use case for what persistence is needed, but also for EFI variables. It, of course, brings a whole lot of new problems because with persistence, we need an encryption and an integrity protection layer for our persistent data. And when we have encryption, we also need an encryption key somehow in the VM, which must not be visible to the hypervisor. So we need to get it via some kind of key broker service in the early boot phase of the SVSM, which in turn requires early attestation. So it's complicated. There's currently a design for that in the works. So we are currently working on the community is currently working on a design document of how to implement that, and the plan is to have this document peer-reviewed by security experts, and then when we agree on a good solution, then we will make progress on that and get to actual persistence within the SVSM. And the long-term vision for the Coconut SVSM to grow into a paravisor. You might have heard this term already. What is a paravisor? In a nutshell, a paravisor is a trusted in-guest virtual machine manager, which means it does not only emulate devices with security-sensitive state, it also handles intercepts from the guest operating system. It can emulate certain devices for the guest OS, and it can also take care of secure IRQ injection. For example, it can filter the IRQs that the host can inject to your operating system, which would mitigate all attacks where the hypervisor injects malicious vectors like int80 or an AMD exception vectors like the VC exception, which has been proven to be usable for attacks. So this can all be done in a paravisor, and when the Coconut SVSM is a paravisor, this can all be mitigated there. This brings us to the distinction between enlightened and non-enlightened OSs. I briefly mentioned that on a previous slide. So Linux is an enlightened OS when it comes to confidential computing. So it has awareness of confidential computing features. It can handle private and shared memory. It has VC and VE handling at the kernel level. And it is being hardened against malicious hypervisor behavior. But this is not true. This is not true for all OSs out there, right? There are OSs that have no real notion of private and shared memory and do not implement a VC or VE handlers themselves. So without an SVSM or without a paravisor, these OSs will not be able to run inside a confidential virtual machine. The good thing is we can outsource all of this awareness to the paravisor, to the in-guest VMM, implement this functionality inside the SVSM, and get the ability to run unenlightened operating systems, or operating systems which are mostly unaware of running in a confidential VM. Yeah. The primary example here is Microsoft Windows, which has some enlightenment, but not much. So running Microsoft Windows in a confidential VM basically requires a paravisor. So. And in paravisor mode, the Coconut SVSM would basically handle all of this. It would be responsible for the interrupt injection. It would still emulate the TPM device and also a variable store and things. But it would also handle guest intercepts, which in turn enables it to emulate devices, because intercepts usually happen also on memory mapped I/O accesses, which is the key to emulate devices in the SVSM via an MMIO interface. So we have a better way of moving device emulations into the paravisor and the SVSM, reducing the need to actually harden device drivers in the Linux kernel. But the need is not fully removed, because especially for device emulation, there's likely a performance overhead involved, because now device accesses go from the operating system kernel to the Coconut SVSM, and then down to the paravisor, which needs to get the data of a disk, for example, and then back via the SVSM to the kernel. So this path gets getting longer, and so emulating devices in the SVSM is less performant but more secure. So. But because of these performance properties, it still makes sense to allow device emulations in the host hypervisor. But for this, we have the device driver hardening mitigation. So this is not a big issue. And with that, I'm at the end of my talk. Thank you for listening, and yeah, happy to answer all your questions now.
How do you envision the TPM attestations, including the TEE attestation info on unenlightened guests?
I'm not the best cryptographic expert to make a statement on that. I think there are ways to do that via the ephemeral key of the basically derive the ephemeral key from the attestation. If we do that, then I think it's possible. Not 100% sure, but yeah, I think there are ways to do that.
Going back to your earlier comments about device emulation, if I understood your slide correctly, there was no need for device driver hardening. Did I understand that correctly?
Yes, if the device emulation is running inside guest context, inside the SVSM, then your device emulation is actually part of the initial attestation and you know what is running. And it's basically trusted code running there and you basically can trust the device emulation. So
the device will still require a device driver, is that correct?
You mean on the guest kernel side or on the SVSM side?
On the SVM.
Yeah, so there still needs to be an interface to the hypervisor. For example, if you emulate a disk device, you don't store the disk data in the SVSM, so this is still in the hypervisor. But this interface can be a lot simpler than a real device interface, and the hardening has to actually happen inside the SVSM and not inside of the guest OS.
Okay. And since you mentioned the kernel side, I'll ask about, is a device driver still required on the kernel side as well?
On the OS kernel side, yes.
Okay.
So,
all right.
The SVSM can, for example, emulate a NVMe device, and that would still require an NVMe driver inside the guest operating system, inside the Linux kernel, for example.
Okay. Thank you.
Other questions?
Hi, good presentation. So my first question is a bit kind of high level. Where do you see this from packaging and deployment perspective in the whole scheme of things deployed? Like this essentially usable in the scenarios where you're doing cloud computing and confidential computing, right? And cloud providers provide their own UEFI image. Do you see that being bundled as part of the image that cloud providers provide, or do you see that as part of the operating system image that are up in the cloud providers' repositories?
So, in a perfect world, the cloud service providers would basically allow bringing your own firmware model, where you can basically deploy your virtual machine disk image together with an IGVM file. And the cloud service provider would load your IGVM file, and you can later see on the launch measurement if your file was loaded and if everything is correct. I'm not sure if that's planned by the CSPs. The alternative is, of course, to have reproducible builds of the Coconut SVSM image. That's also something we are targeting for. So then, in this scenario, the cloud service provider would basically show you the build recipe it used to build its own image, and you can use that to also build an image and compare it, take the launch measurement from that and compare it to the launch measurement the cloud service provider or you get in your virtual machine at the CSP. So that's another scenario. The IGVM file actually consists not only the SVSM but also the firmware. So it also consists contains the guest firmware, so the UEFI firmware usually. It's not limited to that. It can also be, it is very flexible format. You can also have scenarios where you load a Linux kernel directly, for example, but that can all be part of the initial memory image. It is measured. So the question is how this IGVM file is deployed and where it comes from. It currently looks like it comes from the hypervisor, from the CSP, and that would require reproducible builds to be secure.
That's where I was going next with me. Okay.
Yeah.
The second question that I have is about about the TCB reduction within SVSM. I mean, I have been following this project for almost, I think, 2.5 years. I haven't looked into the code, but slowly I have seen that functionalities are getting added on and the size is increasing, which usually is like the cry for security that, the moment you start adding features, there are things which you will keep resolving as bugs, which means that you want it to be able to do some sort of TCP boundaries so that the initial code, which is equivalent to something like on a SOC, a bootrom kind of thing, which is going to provide you the attestation and hand you the encryption key for storage and all, is very less amenable to bugs and updates. So is there kind of TCP separation as well within SVSM?
Not besides the privilege level isolation, so that's the isolation you get.
Okay.
So there's currently also no plan to make the SVSM itself updatable within the guest OS. People might come up with something, but that's not something we currently have looked into. But
okay. Thank you.
Yeah. If there are bugs in the SVSM, you basically, the best option right now is to compile or to get a new version and boot up your VM.
Right, but yeah, my question was more about like, let's say the initial part of the boot up of SVSM, there are no bugs, but TPM handling modules might have some bugs. So because of that, you have to update the entire thing now. So.
Yeah, that's how it's currently planned to do, but yeah.
Thank you.
So all services that the SVSM runs are also part of the initial measurement because the file system image that is deployed to the SVSM memory is also part of the initial measurement.
Yeah.
Which makes it difficult to deploy additional services at runtime because you won't have any measurement or attestation for that then, right? So you would have built software attestation on top of that to make that working. And the same is true for updating 40 modules that are running inside your SVSM. So
yeah, we can talk more about this offline.
Yeah.
Thank you.
Thank you for the talk. Really interesting project. My quick question is about using Rust for this type of low-level system development. In my experience, it requires very often to use unsafe Rust extensions when you have to craft inline assembly, for example. Have you put any thought into how to isolate unsafe Rust code segments in the project, perhaps deprivilege those? So that
no, we haven't looked at this yet. I've seen that there's a Rust kernel project by Intel which implement this, and I plan to look into that and see what we can use of that for the SVSM too.
You might also want to look at the work that the NARCS project did in exactly this. We had a syscall handler with a bunch of unsafe stuff, which we were very careful about how we manage that. So, and that's also a CCC project, so you can look at that. It's also all in Rust. So, yeah, I suggest you have a look at that too.
Thanks.
I was also going to ask, do you have any goals in terms of performance overhead? Because clearly that's one of the things you worry about.
I wouldn't call it goals. Currently, we put more emphasis on security than on performance. That comes from the fact that in its initial mode, where we don't run as a full paravisor, the interaction with the SVSM is actually limited and not happening very often, so performance is likely not a big issue. When we're getting into or at the point where we actually execute as a paravisor, it becomes more of a problem, and then the plan is to look at the actual numbers and see where we can improve. So this is an iterative approach.
And there's also load time overhead as well, which is worth thinking about. Thank you.
Yeah, load time overhead is another thing. So initial things that are measured on launch can be slow. So there is also some effort to actually put the SVSM in non-measured memory and just have a small measured stub, which then compares or which then measures the SVSM in software basically and extends the initial measurement just to get a better launch performance. Any other questions?
So you mentioned a lot about persistence. I guess I was wondering, it sounds like if someone wants to use SVSM for persisting the initial VTPM seeds or the EFI variables, they kind of need to do this handshake with an escrow service. And I guess I'm wondering, for sort of scaling out a cloud service deployment, do you have any thoughts on how that might look? Is this for those customers that really care about standing up this kind of service? Do you have thoughts on like who might own that, as well as like the initialization of that state?
Yeah, this is a big topic actually. It's not only so it involves launch attestation. So the plan is to use the initial attestation to prove to some key broker service that this VM is set up correctly, and then the key broker service will give us a key for our storage. The unsolved problem so far is how the VM does actually prove its identity. So you can have different disk images, and you won't hand out all keys to all VMs, right? You want be sure that it's the correct VM and it's correctly set up before you give it the key, right? And that's currently not a solved problem. So we discussed that in one of our meetings with no clear conclusion so far. But this is part of this will be part of the document that we are currently working on about how all of this initial attestation and key delivery is going to work all together with the early attestation. So this is not a finalized design yet. But that's also the point why we want to have it why we want to have it written up before we actually implement it, because we want it to be possible to do peer review on the document and on the approach we are taking, so that security researchers can look into the document and see, oh, that's how you're doing, and there are this and this problems, and then we can iterate and improve things. And yeah.
Okay, and then can you talk a little bit about the attestation model for a non-persistent TPM? Is it just using ephemeral seeds that are generated and attested to? Like, how does that work?
So this is how it works right now. It basically generates an ephemeral key on launch. And it's the hash of the public key to the attestation report. Mm-hmm. So on SNP systems, you can put like 512 bits of data in the attestation report. And this is where the hash is put for the public key of the TPM, and that is how trust is established to the TPM to a remote party actually. So yeah.
Got it. Thank you.
I think time is almost up. Any last question? No? Then thanks for your questions, thanks for listening, and have a great rest of the day. Thank you.
the time, some of the time, at least rankings, but it's still wildly early from what I understand. So it's been really good by and large. She sleeps from about 11 p.m. until about 7 a.m. most nights, which is wild. Separately from
There is,
no, we did not do anything to enable that. How are you?
as part of
Say hi.
but
Usually required in the US to like allow you to have 3 months, but they're not legally required to pay for it. And so most companies are doing sure, you can take it, we'll give you like 2 weeks paid or whatever. I mean, unpaid leave is nice to have a guaranteed job back, but you also have some new expenses. So,
Yeah.
it's good. It was good first for me taking the I'm to be like, hey, you have to take advantage of that someday. Like for me, it's something that moves the needle a bit. So yeah, so the way Microsoft starts, at least, is so you have what's
Okay.
to the
Right. Yeah, with a pile.
So you're like looking for 600 pictures?
Not 600. I only need 100.
and then, but if you have actually needs birth,
not necessarily.
there's some extra additions. So you get the parental bond.
It's the guest.
So yeah, it's pretty what it is. It's like 2 or 3 weeks of like paid birth recovery leave. Disability. So everyone in Microsoft, US employees, in a short-term disability benefit, if you have any medical condition that started with working, you get 2 weeks or something paid. So I believe that as someone who's physically given birth to a child, you have first a short-term disability, then you have your couple of weeks of gave birth leave, then you have your 12 weeks bonding leave. So you end up somewhere in the ballpark of 16-ish weeks, give or take. I mean, obviously, that's not my situation, so I didn't read up. You get a few extra weeks.
We're all making shit up.
Just to be some country in the world.
If you control the whole stack, it's all easy.
It's wild. I don't.
We're all just kind of like, what do we like? What do you look at our plans? I don't. It's
2 kids. I feel like he was off work. Yeah, it's wonderful. I don't know about the thing that comes to my mind most is wondering how people do it after 3 months of leave. Like, I would not have physically.
You're going to pop back for your mic?
I guess I would have been counting, but it's exhausting. Right? And then finally, we start getting some sleep again. Put on yeah, actually, it's my wife's idea.
it's more that
She likes barely places like known in computer science. She was like, hey, Lovelace, famous speaker and mathematician. I like that even though she's known as a mathematician, like, I don't think her computer world. That's nice.
Well, that's the
if you actually have someone
But you also don't want to, some obscure thing once it's turned on. And I feel like it is like, you don't need another ADA every day, but I think most people are like, oh yes, I've heard of that. That's a name that I've heard of someone.
Oh, right.
Having to deal with other people.
Yeah.
Have a good afternoon.
He has family. Families are hard to keep around. I mean, I say that it's like got my spot. To do what? Yeah, but when I was like really it helped me a lot when we were like trying to figure out like how I that's cool.
Not into the runtime
And
attestation,
I'm excited to see how
my
like
goal with working on rats on Provenance is for there to be a reference
having written like those things so many times, I've done like all the save
so that you
slides
can,
and everything.
so you can have your attestation service learn more about the build to say, oh, it was built with all of this configuration information is okay.
So this is slightly orthogonal to the things that we're talking about, because my problem with this device drivers and things is that I think that bill of material is just way too bigger than the footprint. And there was a hope that we can try to actually. I mean, I'm pessimistic and thinking that the Red Hat and other distros will start to make confidential distros. So and because if they're not doing it, so if they're starting standard distros, there's way too much things enabled with material, which is just we don't pay, we don't need. So you can see, so you, in your way you will be able to see that it's there, but it's.
But you still like kind of need like
the goal is to have an actual policy that will at runtime say yes or no.
And what happens
that policy
if you
can be viewed by
if you don't have that specific
folks who
I'm thinking like because I think that
providing
biggest challenge I had with finding the key for user space
Red Hat.
was
They all
cross-DSM
care about
compatibility.
instances that people will license for use in confidential.
If you don't compile everything with finding
So
the key,
if we start to work on policies that we agree on.
exactly. Yeah, I mean, the way people are like looking at that for IBT, I mean, it was like, if one of the objects doesn't have IBT, just disable it for everybody and then you're going to be happy. But,
yeah, that would be one way if actually, if the distros are ready to go with it. That's, minimizing the distros part.
Yeah, that's nice, yeah.
There's a lot of
Then
things.
you don't cross this.
So if there's a way to push that direction, it's great. But
Right, so the
it
more
has
you
to-
turn off, the more people are unable to do it.
But do you have like a,
But
there
a
are-
lot of
there-
this,
let's say
like
course grain kind of control for like
drivers is
static
where we're just doing mouse
and net range that accepts for value?
Right,
sitting there.
right.
So
So,
never in confidential computing will be needed.
yes.
No, yeah, I mean,
I
if
think
you
it's
want
going
like
to
to
take
land on
a
the
lot
net
of
range,
us
but if you
working
want to land on that
with
specific net range, trust, whatever.
These configurations are
Okay.
not good for the confidential offering.
But it's the interesting part that like we will have a layer, not just configuration layers, just like what I already have. We just need to agree what's the minimal configuration, but you also will have a
And
layer
are you
that's
also like handling
where if it's trusted
speculation?
we work. So we will have a way to say that okay, regardless of configurations, we will allow these devices to access our memory and stuff. So why we can't? And this is going to be a runtime decision, and it's going to be a decision by not builders of the distro or anything. This is going to be a customer decision. So this is also like this goes back to just saying what we won't be able to say.
And when
it's
you
not
have
just
like a
about
fine
this
between place, you're like no memory access
but about
for
all
doing
devices.
Yeah.
the whole
So
kind of
and
check.
that
So
is something
that's
that
really
distros won't be
fast
able
to
to
check.
provide us.
So
I mean, they may be able to
you get
provide
like
us configuration. This
there's
is
still
really
like
a
race condition
runtime
there,
choice.
but you get like a little bit of like a more kind of like
Maybe I trust this
for the
number of trusted
for
devices
speculation
is the
season. That's
certificate measurement chain. So
that's something Intel was like
expected to be,
excited about.
and I
because
might
he
trust,
figured it out.
CSP running certain settings, let's say networking device. I'm
Okay.
using the data layer protection. My data is safe.
basically
nice.
the distro.
Nice that you guys are doing it like the right way.
So
The image.
There's
But again, the policy, again, for trusted cloud devices, the
There's a
policy
tiny
is not
thing
going to
about
require
IDP
the
that concerns me.
you know, whenever you decide, you know, if
when
this,
you-
you're going to make a runtime
Get
decision.
like an interrupt.
You know, is this certificate and measurement chain and what's not is something I'm okay with, or is this, you know, running maybe old compromised version? This is not something distros will take.
right, that goes into the application verification. That's where policy comes from. I don't think that you're going to be in a situation where you do not accept
Yeah, but the thing is,
device
if
before that.
it is an MSR,
You're going to be,
but
do
it's
this
a state machine, right?
setup
So you should get
part
like
where
an
you don't release any secrets until you have
you need to basically drop that state machine.
and then once that is established, you ask for
Yeah,
the
but you were like in kernel
evidence.
mode, and now you're
in order
like
to-
in another kernel
Right,
mode.
but
What is
that
that?
happens
Sort of
early,
like nested
it should
kernel.
happen early now.
Yeah,
Yes.
That should happen
but I mean, it's really hard to.
before we start, you know, logging these drivers. Because if you allow the drivers to, you know, start going all the pro functions and things before you have verified anything, things can already happen. So, I mean, bad things can already happen, so
You still have to perform attestation, read the evidence, and that's trusted.
Yeah.
That's a trusted process. If it's tampered with by the devices, track that.
So the trusted devices, not the rest of the devices.
There's the Rego policy language for the open policy engine that exploration attestation verifier service is targeting, so that you can say I have all the specified logic to accept or reject particular claim.
I mean, but if you think about it, I mean, it's a problem that
You
regular
can
CFI
come
laws
up
are
with
having. Because
rather sophisticated
yeah.
because someone makes the decision of whether
No, I totally
something
agree.
is
It's like
secure or
super
not.
complex and hard to execute.
Part of the
But I mean, the thing is, if you think about software,
Yeah, no, I'm sure, you know,
software-based
technically we
CFI,
can do it.
you
The
were like
problem is that,
basically
like, I think
references
it's, you know,
pointer,
device
checking the
policies
tag,
and things, but
and
all that,
if you get an
I think
interrupt,
some of the part of the community then
contents of these registers, you're going to be like a A flag.
problem. So I think, we're going to have trusted devices.
So somebody
running
could
with
go and
registration
change
and
it to
everything.
fixes.
And they're good after that. So, but we're forgetting that, like, you know, there's this other
Yeah, that's a-
drivers which are there's other classes, and they can be used as
Yeah, I mean,
alternative.
Just to
All sources of untrusted
Yeah.
data from the host do need to be removed.
Yeah,
or
Yeah,
It was
and
nice
this
working
is
on
what
my
we're trying to see is like, how do we do it correctly for drivers? You know, if distros are ready to code flashing computing, take configuration.
Yeah, it was, I mean,
But publishers, nobody
now I
has
can
been
teach you.
able. We don't have like, we haven't done like, you know, when we did the buzzing thing, we haven't, you know, a couple of research papers which did it, which, you know, they went into certain sort of drivers and we just found, you know,
To be honest, I mean,
vulnerabilities in
version driver keys, I discussed that with
we have only
RISC-V
passed now
manager
the
at Microsoft already. So we were like having a conversation and I brought
because
up,
we
yeah, I
didn't
worked on
need
this
anything
project.
else and we disabled
At
it.
the
I know
point, I mean,
Google
we
worked
presented
and
finally
some other things.
Yeah, we don't even have
they were like,
Yeah, no, I'm just saying with like, you know,
I honestly
you were
don't
able
know
to
if
harden
it was
your
because of
drivers and so on, but who's gonna find time?
jobs or
Resources to go look at
because they
all
really
the things
prefer
which are
XFP.
enabled.
And you're
But
like, yeah,
apart
I
from, you know,
totally
the
understand that risk would
researchers
happen.
and say that, okay,
Protected.
it's,
Okay, so come at it from the end of,
Yeah.
we have the most minimal configuration that we can do something useful in, perform a diff.
But yeah, I mean, it's a thing, I think that, there's
we
a
haven't played this
strong
config
point
because
to
this is
make
what
for
we did
Microsoft's
to
case,
disable
like
these
compatibility,
drivers
like
in
bitmap thing,
runtime so because
which
it
is
was
complex
easier and
and
it will work.
make it work.
And this was our minimal. We run literally
I never tried,
5
so
virtual
maybe it's not that hard,
devices,
but
virtual PCI device,
people
that was all.
told me
we've run with typical distro, and this filter enabled.
The bin map, because I mean, you have
We
like
didn't have,
IBT,
we didn't have to worry.
basically all
Yeah.
Removing the
processes need to be
devices
IBT.
after attestation, you could already
And all
have
the processes, no, sorry, all
done
the libraries
their
need to be
damage.
IBT
No, this
enabled.
was
So
during
the same thing we
the,
were talking about across the
beside
SO earlier.
discovery. So this would be when you do it beside discovery guest. You're just checking, you found the device, you're checking if this device has been authorized by policy, and if it hasn't,
you
you're
can,
not,
I
the
mean,
probe is not going
there's
to
still
run
like some sort of
forever,
compatibility,
the probe is not
like the
going to
client CFI also has like
So this is like, this is not too late.
So they can still like kind of make it
too late in
work,
some cases for initialization functions.
weird,
Because driver initialization has been built in. This is going to run before, because this runs before when the driver is discovered. And we found cases where, some older legacy drivers would go and do something to set in this phase.
They let anybody into this place. I'm here.
So, sorry, I was just...
It's fine, good.
So in some cases, the new functions can go.
When I was doing it, I remember this
much smaller subset. The most important is just to probe and then
the guy
this is our kind of finding result. That's why we want to find
he needs it. And he's now he's not trying to push for IBT
and
users
the big
based on
distros
something
are
else.
going to be trying to satisfy the most people, which is going to be less secure.
I remember that Peter was like,
So there are going to be startups that are like, we're the confidential computing distro.
let's take a look at that.
Like there's already the opaque systems, edgeless, and other folks, Organics, they're kind of like their own specialized environments. People do care. And in order for it to become more mainstream, people have to start using technology. I mean, we are a cost center.
Well, and so like I do a lot of work in OpenSSF, and in OpenSSF, one of the things we're going to be pushing is using confidential computing to make sure that you have a very good handle on the provenance of your workflow pipeline. Make sure that
I do like the scorecard.
yeah, I love scorecard. We're using it all over the place in Intel right now. Fortunately, I'm pissing a lot of people off. But I think confidential computing is going to have to become more mainstream than it is right now.
So on the topic of like trusting actual builds, it's not so much just like you have a container and different source. Think about it like chocolate. It's the entire build pipeline. There's a system that combines those two things and provides the security environment. And that's going to be some special sauce that people don't So I could provide a transparent build in our U field. It wouldn't matter because we wouldn't have a transparent build of the entire build system to show that it all worked out.
I think because at some point was hinting and asking questions.
Yeah,
But
so
this is not going to happen.
I'm really trying to make the build reproducible, not just well documented what happened.
There's not enough people that actually do reproducible builds right now, so I'm so happy to hear you say that.
Yeah, I understand. So we have someone who builds EDK2 for his and has lots of ideas on how to make the upstream build configuration deterministic. We have our own deterministic construction build system.
In the end, I mean, there's all like a trade-off, right?
And I could, as part of our transparent publication of our report, show that we're building with Bazel and use that as a
hopefully things are going to be better.
I don't know if that's going to be what people want to see, because they're going to want to know that there's very minimal difference. We have to turn off PCR0 measements for the firmware and for ACPI tables because those change every time we VM from whole. And yeah, so we have a very different story for providing
persistent disk and firmware. So when you
got the wrong right
pause at the end, you can't actually pause the confidentiality. It snapshots what firmware is currently there, or when you read, the firmware stays. But if you shut down, then bringing up a new VM is bringing up a new machine. You're going to get the firmware that we rolled out. We do not have a way of pinning to firmware, nor would it be a wise decision to pin to firmware. So we have to make it like a whole rigmarole of, oh, we're going to revoke our claims of this being a good version for when you're doing application services.
Okay.
Signed endorsements of these firmwares when you're doing this verification. We need to provide a more stable source of what firmware is, what you're going to get, because you get whatever you get right now. So there's a lot of control framework that I would need in order to put in the particular firmwares that people choose. Choose up to. So that we can say this is out of date, please go get something new, and then you can actually go look at the ones that are new, update your TPM policies to accept those measurements, and then you go and use them. But if you do anything other than that, which is what people do today, then PCR0 would not be stable, and then you would wreck it.
Pardon me, my good friends. I'm going to be coming through here with an ice cream freezer to entertain you guys a little later, so bear that in mind.
Lactose intolerant. Lactose tolerance is the weird thing.
Just talk to Case real quick. Are you anything going on for dinner tonight? I was going to try to get Bill in case he can go to dinner.
I'm going to say if I can talk to just the people that I'm talking to.
I don't know. Let me figure that out and I'll let you know.
No, not fair, no.
No, I was thinking like 7 o'clock or something. I could do it earlier too. Yeah, no, I get that. So I will try to make sure. Yeah, no, because I don't get to see you nearly as often, and it's really good to see that. Yeah, no, we didn't really get a chance to.
Sure, go talk to kids.
Hey, how you doing?
How's it going?
Good. Keeping busy?
Yep.
Cool. It's good to see you. Cool.
All right, is this thing on? I think I hear myself. I'm going to go ahead and get started. It's 11:10, so after the break, I see people still coming in. So wait a second. All right. Hi, my name is Case. I'm going to be talking about our attempts to mitigate integer overflow in the C in Linux kernel. I've got a link to the slides at the bottom here if you want to follow along, or click on the links that I have in there. This is all part of the Linux kernel self-protection project. And so let's just dive in. So the main question is, why do we care about integer overflows at all? And honestly, it's the root cause of a lot of security vulnerabilities. You know, we have mitigations in place to sort of catch the effects of overflows and catch the effects of these things. Like control flow integrity is sort of an after the flaw has been attacked kind of fix, whereas this is going after the root cause. This is really difficult to get rid of in C because of a lot of surprising behaviors that exist. Other languages have dealt with this head on. You can see like Rust has explicit wrapping types and things like that. But the main takeaway is that, at least in Linux kernel, everything we've been doing doesn't really seem to be making much of a dent in integer overflows. I grabbed a bunch of CVEs over the last 10 years and just sort of grepped for overflow in anything that was listed as like medium priority or higher. There's hundreds and hundreds of low priority stuff that's questionable for an analysis, but you know, we haven't really made any changes meaningfully in the kernel in the last decade for this, so it's time to start fixing it. And a lot of this really depends on the nitty-gritty details of memory layouts and other things, so I just want to go over, you know, what is an overflow? And the best I've been able to describe this is having a calculations result exceeding the representation range for a given variable. In memory, like we've got an 8-bit unsigned storage, the bit just walks off the end, and there's nowhere for the 9th bit to go, so we end up wrapping around. It's like you know, modular arithmetic. And for signed stuff with 2's complement, as that bit walks further and further up, eventually it gets the last bit, which in 2's complement means now it's the sign. So we wrap all the way back around to the negative values. So this is the overflow condition that in memory. But for a language, for C, what really is going on is we have overflow resolution strategies. What happens? What can a compiled language do about an overflow? One option is nothing. Don't just do whatever the machine code does, which is sort of what that prior slide was. And that's why we think of this commonly as overflow means wraparound, because that's the effect we see in standard memory. And so the other is to explicitly wrap around, to say it is defined to wrap around no matter what the storage mechanism is. Another resolution strategy is to saturate. At overflow, you simply do not go beyond the maximum value or below the minimum value. We have an implementation of this in the kernel in ref count T, for example, which won't go, it'll basically saturate at an invalid value. The other one, which we're going to talk quite a bit more about, is trapping. Once you reach an overflow, you say, we were not expecting this, we can't handle it, kill this thread of execution, we cannot continue. And then the favorite one, of course, is undefined behavior, which is pretend we don't know what kind of CPU we're running on, treat the result as undefined, and let compiler optimization passes do insane things. So in the C standard for unsigned, the C standard explicitly says, unsigned integer arithmetic overflow must wrap around. All our memory systems already do the right thing for free. This is easy. We depend on it. If there's some weird machine doing ones complements or something, it would have to actually do the logic to explicitly wrap around an unsigned value. But we'll come back to unsigned wraparound later. Most of our problems come with the C standards dealing with signed integer types. And everyone just loves to type int in C. It's the shortest. C standard says that overflow for signed types is undefined. And this was in theory for trying to unify the C language across lots of different machines that weren't necessarily all 2's complement or whatever, but this is absolute ancient history at this point. In practice, for our systems, what this used to mean for undefined was effectively a none strategy. So we would get the wraparound because that's the type of system, the 2's complement system we were on. However, with modern optimizing compilers, we now have undefined behavior means let the optimizer hallucinate. We can take a look at this right now. There's a relatively common C code pattern for checking for potential overflow by looking for wraparound. So if you say, if some value plus an offset is less than the value was, we've clearly wrapped around. And this is like, oh no, okay, we should reject the wraparound. And if we don't, then we're going to do things knowing the offset is safe. And then we maybe perform the calculation or do something else with offset knowing that we're fine. But after optimization, this effectively just gets thrown away. Oh, that's an impossible state, or it's undefined, and just get rid of it completely. This first hit the kernel in 2009, and what we ended up doing was doing -f wrap v as an option, which says things are going to wrap around for sure. This is included in what we use now, which is -f no strict overflow, which is a very strangely named option. But basically, this turns on. It forces a wrapping behavior for signed types. To give an example of what this looks like, if you were to build with -02 this thing where we say, if value plus offset is less than value, then we can turn one string pointer, otherwise the first one. If you look at this code that's actually generated, it never looks at value, which would be in DI. It only looks at SI, so you just get a completely bizarre behavior that has nothing to do with what you actually wrote. Not great. But if you build with -f no strict overflow, then it actually does do the calculation and test against DI, which is exactly what we want. And so getting rid of undefined behavior was pretty important because more than a security issue, it just causes crazy things to happen. So now, hooray, everything will overflow. Not exactly what we wanted, but at least arithmetic works in a reliable fashion. The good news is that for catching arithmetic overflow, we do have sanitizers available in GCC and Clang. There's the fsanitize signed integer overflow, which is the main one, and then Clang actually has a sanitize unsigned integer overflow checker as well. There is also pointer overflow, but I'm not going to talk about that today. It's yet more of the same of these two. The sanitizers effectively have two modes. You can warn about the situation and continue execution, which is mostly as a debugging option, or you can actually trap. You can stop this sort of execution because we don't have any kind of handling of these situations in C naturally. So the only thing we can do is just freak out. We can see an example of this. If we're using the signed integer overflow checking here, we've got int foo set to int max, and we're going to multiply it by how many arguments we've got. So down below, if we just run foo, we get the result of int max times 1, which is fine. And if we add another argument, then the sanitizer catches it and says, hey, look, int max times 2 cannot be represented in the int type. You would lose bits off the end. But it continues and shows us the wrapped value, -2. OK. If we're using trapping mode, we don't even get the report. It just dies straight out. It says, this is very bad, bad situation. So this is great. This means we could use the signed integer overflow sanitizer to catch overflows. Except it doesn't work with -f no strict overflow. So because it's not undefined behavior anymore. It's been defined to wrap around. But of course, the UBSAN unsigned integer overflow checker doesn't break and says, oh, an overflow did occur, even though it's defined behavior. So my head is spinning. The signed integer overflow sanitizer only runs when it finds undefined signed integer overflows, but -f no strict overflow makes it defined, which disables all the checks. And the undefined behavior sanitizer named unsigned integer overflow finds the overflows, but they're always defined for unsigned types using the wraparound strategy. So neither of these things are named correctly. But the point, the main takeaway is, in the real world, we don't care about any of these details. We need to be able to instrument overflows, no matter what the resolution strategy chosen by the compiler is. We care about the result of that calculation. Did it do something we didn't expect? So in that regard, I kind of want to rename the undefined behavior sanitizer to unexpected behavior sanitizer, because I want to catch the places where we are doing something unexpected. So again, repeating, the signed integer overflow sanitizer needs to detect overflows regardless of the resolution strategy. This has been fixed in Clang now. Clang 19 probably won't release till September. But if you want to play with Tipitry on Clang, the sanitizer, the signed integer sanitizer will work here. In support of that, Linux 6.9, which is not yet out, does re-enable the sanitizer so we can start playing with it and finding where we're going to have problems. GCC still does not handle -f no strict overflow with its sanitizer, and the unsigned integer overflow sanitizer hasn't even been implemented in GCC. The main issue here, of course, is a social issue, not a technical issue. And I've been trying to convince GCC developers that what we want is overflow sanitizers, not undefined behavior sanitizers. Like, undefined behavior is nice for debugging the C standard and how you follow it in your code, but in the practical world, and at least in how Linux operates, we don't want undefined behavior at all in any place in the kernel. It just asks for trouble, but we do want to find overflows. So trying to get that shift of mentality and just make it work correctly the way we want it to. OK, so remember about open-coded overflow detection? Remember this situation? So now that we've fixed the sanitizer to work, it'll actually trigger if offset exceeds value, which is what this test was trying to find, which is not great. So we need to we need to identify these code patterns, and we've got two ways we can solve it. Either we can refactor the code and not do that. And this is probably best for signed types, because they have this history of undefined behavior, even though we don't actually have undefined behavior. Or we need to teach the compiler to recognize these, the need for these kind of idiom exclusions. And this is probably going to be more important for the unsigned types, because people have, for 50 years, been writing wraparound with unsigned types. So refactoring the signed type stuff, we can use the check overflow helpers, which are really just a light wrapper around the compiler's built-in operation overflow helpers that will let you know if something overflowed. So the prior example basically says, if I'm going to use the result of that calculation later, let's actually use checkout overflow, since it'll take, in this example, value plus offset and stick it into result, no matter what, even if it wrapped around, and we can actually use result later. Otherwise, we can actually rewrite this to not do an overflow, but to actually just check the math on it, which is to say, if the offset is greater than the difference between the maximum value and the value itself, in other words, how much is left before you go past the maximum value, then it's an overflow. So we can actually do the test without triggering a wraparound in the runtime. And there's a bunch of these in the kernel, so I'm lazy and I like to use coccinelle or the semantic patching tool, spatch. So I have a rule here, look for var plus offset less than var, we can replace it, or var plus offset less than 0, we can replace it. But again, we're still going to need to have to teach the compiler about this situation, especially for the unsigned types. This is probably going to wait because we have other things that we need to do, and we want to nail down having the signed integer overflow stuff actually working reliably in a way that we can move forward. But this is on the list for us to do. The main issue, probably the largest difficulty with dealing with wraparound in C is just answering the question, was this operation expected to wrap around? Because looking at open-coded math in C, there is no way to tell. It is ambiguous. When you look at it, you go, I don't know what the developer wanted here. Some places this is easy to deal with. If you're trying to allocate memory, you really don't want to wrap around. That one's straightforward. If you're doing, hashes or other crypto and all kinds of other things where you're doing modulo-style operations, then yeah, you're expecting it to wrap. You're expecting it to do those kinds of things. And sprinkling the overflow checking helpers all around the code in every single operation everywhere. How about, look at one function of a hashing routine. You're going to add, check mul overflow in every single line where it's doing 20 operations to, cycle a value through. It's going to become unreadable. We need a way to disambiguate these operations. And one of the ways that we've done this traditionally, both in C generally and in the Linux kernel, is adding a type. GFPT used to be an unsigned int, so now we can actually do type checking on that. Time t is, of course, changing its width. Like, we've got things to do this. So we need to create wrapping types. So to reiterate again the approach, we can check for wraparound with the sanitizers, but to allow for wraparound, we actually need to disable the sanitizer. Granularity is currently pretty poor. You can either turn it off for an entire directory in the kernel, or you can turn it off for an entire file, or you can turn it off for a function, or you can use the explicit wrapping helpers on a per operation basis, which is really irritating. But if we actually have this type, we can apply it everywhere automatically and with one annotation. So the solution that's being worked on is actually a typedef attribute, just named wraps. So in this example, we could have typedef unsigned int with the wraps attribute, name it u32 wrap. And now, when you have these operations, the compiler knows it's expected to wrap and it'll disable the sanitizer. And other developers looking at this code will say, was this meant to wrap? And they look at the types and go, yes, it says wrap. Look at that. Very easy. So there's a C implementation, or a Clang implementation up for review right now also from Justin Stitt. And this works quite nicely and makes the annotations and refactoring way, way lighter within the kernel. So it's question time if you've been paying attention. With the sanitizer enabled, what happens at the end of this while loop? Let's see if anyone offers up an answer. Right, the sanitizer will say, oh, you've hit the end of the, or as you're going through the while loop, you're decrementing num. And it says, oh, num is 0. We're done with this loop. We'll exit the loop and decrement num. Oh, we've now decremented below 0. And the sanitizer goes, blah. This is not intended at all. No one wants this. This is just bad. So we can avoid this either by using, in this example, U32 wrap, which is irritating, or we just refactor all these while minuses to a 4, which separates the test from the decrement. There's only 1,000 instances of this kernel. No one will murder me if I try to send that patch. But it's really best if the compiler can be taught to avoid this. Like, it should be able to see, oh, we're never using num again. I don't care about this. So this is another idiom we need to exclude from the sanitizer to make it actually usable. And then, of course, for the unsigned sanitizer, we have unsigned negative constants in the kernel everywhere. This has been a long-standing shorthand for saying set all the bits. Just like, I want all the bits set for this value, for this variable, or occasionally slightly less than the maximum value. So looking at all the cases where we have -1 unsigned long, we could certainly replace this with ulong max. It gets weird, but that's sort of tolerable. But then when we have like -2 ul, it's like, okay, we're slightly below ulong max -1. It's starting to get more and more ugly with these replacements. So probably we don't want to do refactoring against the kernel. Once again, teach the sanitizer, just ignore this. You've got an integer constant expression. We meant the value here. Like, this isn't an accidental problem you need to warn me about. Just, actually give me the unsigned value for that. And that replaces a whole bunch of other places or that fixes a whole bunch of other places in the kernel where the unsigned sanitizer trips. So now we're ready to catch flaws. So here's an example, very recently fixed, 32-bit wraparound in an IO control. So we're dealing with a U32 that is coming in as an argument and being multiplied by basically anything other than a 1, which means this can wrap around. The allocator ends up allocating less than was expected. And this isn't a case where we would run off the end of memory before it became exploitable. We actually are doing a minimum bounds on the loop that populates the resulting allocation. So even though there is this huge num of nodes that came in, we can actually control that we're only going to affect a smaller portion of it. So as long as the NPDDS is larger than the allocation size that we tricked it into allocating, that final PAI is going to wander off the end of heap memory and do things. And of course, the sanitizer catches this. It's great. Though for note, config ubsan bounds also catches this. It catches it at the point of trying to go past the end of the array. Unfortunately, that's just kind of good luck in this situation because both the allocation and the array access are happening in the same function, so the visibility is there. So better that we actually catch it even earlier than ubsan bounds checking. Also go read about the counted by attribute. That's a whole other topic. All right, so we're ready to catch flaws. So here's another overflow fixed last year. We've got a U8 number of elements. We walk this list, counting how many we have, so that we can allocate enough space for how many we have in the list. And then we walk that list again and set those values. But of course, as it turns out, the integer overflow sanitizer does not catch this. So what's actually happening? So we've got a U8 that's 255, let's say. We're going to do num plus plus. This is actually num equals num, and then at the end there, +1. But because the type size is smaller than int, it's promoted to an int. So int num, and now I've got a much longer bit representation, +1. So this is 255 as an int, and we perform the arithmetic And the sanitizer says, cool, we've taken an int from 255 to 256. Everything is great. You pass the check. But of course, this is being assigned to a U8, so it gets cast back to U8, truncates the value, and we die with effectively a wrapped around value truncation. The good news is the folks developing the sanitizers were not completely ignoring this, and we have even more sanitizers we can turn on. So the implicit truncation sanitizer can now also be added to catch more of these cases. The implicit signed integer truncation sanitizer is going to catch the vast majority of these problems because of that implicit integer promotion that goes on in C all the time behind the scenes. There is the unsigned truncation as well. Now, of course, when you do this, then suddenly you have a resurgence of the while whatever minus minus problem, but as it applies to types smaller than int. So again, we can refactor it by changing it either to a signed type where we don't care that we wrap negative, or we do U8 wrap. But really, as before, we just need to teach the compiler. We don't care. We wanted this. Like, do what I mean, not what I said. So the summary here is, like all the steps I listed earlier, was we want to fix the integer overflow sanitizers to work with no strict overflow to begin with. We've got to refactor the open-coded signed integer overflow test, teach a sanitizer about that style of open-coded overflow detection, create wrapping types so that we can start fixing these cases everywhere within the kernel, which is probably going to take a while because there's a lot of unsigned variables in the kernel. But that's the plan. We have to do it. So we might as well get started. I think what's stopped people from doing this for a long time is that we had no way to mark variables. We couldn't do type, we couldn't show that kind of information about the type. So with the actual typedef attribute, we can start making progress. Teach a sanitizer about the post-decremented loop variables, teach it about unsigned negative constants, and then turn on the implicit truncation sanitizers, and then continue refactoring. I'm going to have some water. So looking into the crystal ball for the coming year, Linux 6.9, probably coming out in May. We've got now the config ubsan signed wrap for testing. It's off by default because it has known false positives. We've been throwing syscaller at it, and it spits out a bunch of stuff in like VFS layer and some other places where we have the kernel loves to mix int with things that it didn't really mean were int, but are probably smaller than U16, but we just used int because it was easy to type, 20 years ago. So there's all these weird mixtures where we're passing an int down into things that are actually unsigned and doing strange stuff. So the sanitizer actually finds these, and just cleaning them up actually makes the code significantly more readable. It disambiguates a lot, makes things much clearer. But we still have to go through that and find them. Linux 6.10, we will have addressed all the syscaller false positives, sure. And we can actually turn on, make the signed wrapping more widely available. So, get the actual syscaller, sysbot dashboard that's always running, sort of sick that config on syscaller, the public syscaller, and hopefully we will not drown people in reports by this point, since we'll have found the low-hanging fruit. And then later on, in September, we should see Clang 19 be released. We have the integer overflow sanitizers working with -f no strict overflow already. That's landed. We just don't have a released version of it. Wraps is up for merging. It hasn't landed yet, but we'll have that wraps attribute by Clang 19, almost for sure. And then we start working on the idiom exclusions, trying to teach the compiler about not making us crazy. Then for Linux 6.11, probably in November, we're going to turn on the unsigned wrapper, which is going to be much more exciting. I have a series of something like 100 patches where I don't know, I spend my weekends doing this kind of stuff, I guess, which is I'm eating dinner, watching TV, doing whatever, and I've got the laptop next to me, and it's doing a build, and I boot it with the unsigned integer overflow sanitizer. It boots up, it immediately crashes. I go look at what that thing is, I fix it, let it build again, go back to eating, and just like cycled back and forth, fixing stupid things, and eventually going, okay, I'm going to exclude the entire crypto directory. Okay, I'm going to exclude all of networking right now because both v4 and v6 love doing crazy things, again, with confusing int and not int. And just, I end up with like about 100 patch series. It actually boots. I get to a shell. There's no warnings. Everything's happy. Looking at the result, though, it kind of feels like I basically just turned off the sanitizer everywhere. So I think once we get to 6.11 and we've made some more progress with idiom exclusions, we'll actually end up with sort of a reasonable approach where we're not just turning off the unsigned integer overflow sanitizer. So I'm hoping that by 6.11 we'll have that for initial testing. And since that'll be November, following the Clang 19 release, we can start actually using the wraps type attribute to start fixing things. So another place, I talked about hashes and sort of networking and VFS and some other things. But another one is actually timekeeping. There is a lot of weird math where you're trying to say, oh, yeah, that timer went off in the past. I guess it has expired. Let's move on. So it's actually expecting to wrap around. So one thing we could do is if we make jiffies, mark it as a wraps type, all the rest of the stuff that's working against jiffies and other timers will naturally wrap around without instrumentation. Anyway, so progressing through that, we get unsigned wrap for wider testing. And then we bring in the signed truncation sanitizer for initial testing and continue fixing false positives. And then when that gets moved to wider testing for 6.12 sometime in April of next year, and we do the unsigned truncation. We just sort of continue progressing through these sanitizers and make this transition. So that's the whole plan and all the hiccups we've run into so far and the solutions we've got. So that's all I've got. If people want to ask questions, come on up.
Hi, Case. I wanted to ask about the implicit conversion on assignment to a variable halfway through, and you addressed part of that.
Yeah.
It's not clear to me, does the sanitizer also catch things like assigning an unsigned value into a signed value of the same size, but outside the positive range? Okay, like assigning a 129 to an 8-bit signed integer.
Yes. Yeah, it does catch that, which is good, which is why, yeah, that's the first line here is like the implicit signed integer truncation thing actually does a lot more work as far as checking because it's doing that logic. It's saying, oh, whoops, did we touch the signed bit? So it ends up like turning that on. There's just another boatload of warnings.
Okay, so that means that would be the end of an unmarked char. Like, if you don't specify signed or unsigned, it's implementation defined.
Yes.
And x86 defines it as signed, and ARM defines that as unsigned.
Yes.
So all char types should now have a signed or unsigned.
Yes, and luckily we sort of bit the bullet on that one, and we define car as unsigned in the kernel now, as of about a year ago. And we had some fun with problems, but we sorted it all out because we kept running into that. But yes, for car itself, we've thankfully made it defined now. Because again,
okay, thank you.
Yeah, we just want to stamp out the undefined behavior in the kernel. All it does is cause us pain.
Thanks for the presentation.
Yeah.
So I apologize for mentioning Java, but I do know that the JVM has a handler for when you get like a SIG floating point exception. So how feasible do you think it will be to have some sort of mechanism in the exception handler for arithmetic exceptions in the kernel at runtime?
So C doesn't really have a great story for doing that kind of exception handling. Doing all of this in C++ is actually pretty easy because you can overload operators. And you can make a new type and just overload the operator and say, yeah, this is wrapping and that one isn't. And you can define your exception handlers. You can do all this. It's much, much more flexible. C doesn't have anything like that. And in the kernel, we're not in a good position of like, so what do we do? Like, right, I've overflowed. Like,
even if you know which instruction caused it, at that point is undefined or it's just
and so like that's why when dealing this, we just have either yell about it and continue, or trap. Let's see where I got somewhere here. Yeah, the only things we can do with the sanitizer is just warn and continue with that overflow, which is nice for debugging, but doesn't help too much. So it gets us a situation in the kernel where you can ship production code, so like distro kernels can turn this on, which is what we have right now for UBSAN bounds, for the array bounds checker. You emit a warning and then continue doing whatever disastrous garbage is going to happen next. Anyone who is super paranoid about the system state can set panic on warn, or they can set a warn limit. Like the kernel can warn this many times before it panics. And that's to give us this flexibility between what do we do when we hit that situation, because there's, how do we resolve it? It's unclear because the author of the code, maybe they wanted to wrap, maybe they didn't want to wrap. Well, we can't really choose. So we actually have to choose to wrap around or choose to freak out permanently.
Thank you.
Yeah.
Hi, just one last comment there. For the sanitized trap mode, we actually found that to be really useful for fuzzing, not generally the Linux kernel, but more exotic embedded systems where the build systems are insane, like EDK2, for example. It's just way easier to add a compile flag than to actually link in a runtime. Only issue we found with that is that during fuzzing, once we find those issues, it's hard to actually tell them apart, which undefined behavior actually occurred. So if there are improvements being made to undefined sanitizer, it would be great that the trap mode would actually load some type of ID into a register before it actually traps, so that when the trap occurs, we can tell which undefined behavior occurred during fuzzing. So this is really a comment to anyone in the audience or anyone watching this video later who's working on the compilers. It would be awesome to have that. So.
Yep. So what's interesting is for the way the trap is implemented on x86 is the UD2 instruction, which is 2 bytes and you're done, you just die. You have no idea why or what. On ARM64, because of the fixed instruction sizes, there's a ton of immediate bits available. And in Clang, not in GCC, in Clang it actually encodes what sanitizer and what sub-sanitizer is causing the trap. So right now in the kernel, if you do a config UBSAN trap on ARM64, you will actually get a meaningful splat. Like it'll say, oh, UBSAN array bounds, and where it happened. Like you won't have any other context. You won't see what the variable is. You won't any of that. But at least you'll have context about what was happening. And there's actually someone as of last week trying to find the right solution for this on x86, which is to either, instead of using UD2, use UD1, which has a wider bit space, and do the same kind of encoding on x86 where we get that. Or do what we do for other trapping mechanisms, like right now for the kernel CFI, every time a CFI trap location is emitted, it will record that address in a separate section so that at trap time in the kernel, it can go check that table and say, oh, hey, this address is actually in the KCFI table. This was a KCFI trap. So we could do that also for the sanitizers and say, oh, which sanitizer is this, and check all the different tables.
Fantastic. Great to hear. Thank you.
You're welcome.
I love that you care about integer overflows, so just thank you.
Yes. Someone has to. Cool. Well, thanks very much. I'm around at the conference if you have any other questions, or you can email me or anything else. So thanks.
Mic testing, okay. Looks like it works now. Okay, so yeah, I'm here to talk about control flow integrity on RISC-V.
It's on now.
Most of the time, people used to call something like debug, and they said it like they're saying my name. And a couple of people actually gave me the name, so it just stuck to me. So I just go by the handle debug in case someone was curious. I'm a security engineer at Revos. It's a startup which is working in data center space, trying to use RISC-V architecture to target certain enterprise workloads. Previously, I did security engineering at AWS, Intel, and McAfee. Mostly worked on like security for foundational technologies, or at Intel, I worked on ISA definitions like Intel CET, short for control flow enforcement technology, or defining hypervisor enforced linear address translation, which is primarily for things like mitigate against page table kind of attacks. And of course, everyone here has probably worked on side channel mitigations. So don't have an agenda slide, but we're going to talk about what is CFI, and most of the people over know about it. And then we're going to move on to some RISC-V specific stuff. And then we're going to talk about how RISC-V architecture is trying to solve the problem. And then what is the status on like enabling in kernel and software. So first of all, what is RISC-V and why RISC-V? RISC-V is an open standard instruction set architecture that came out of UC Berkeley. 5 basically stands for the 5th version. It was created at Berkeley for primarily education and research purposes because there wasn't any open source ISA until at that point of time. Why? Because you don't have to pay a lot of money to ISA stakeholders. And the other reason is the ISA has been developed in such a way that it is extensible and composable. So you can pick and choose. It is governed by an organization called as RISC-V International. And most of the industry partners basically become member organizations of that, and they collaboratively work together to make new ISA extensions if they need one. So it's kind of a open source for CPU design and things like that. Memory safety, we just saw Keys talk about unsigned integer overflows. That's where it starts most of the time. And it ends up being touching invalid memory, which usually is good if it crashes, because that's when you have only denial of service. But if someone knows about such bugs beforehand, then what they can do is they can hijack the control flow and perform remote code execution kind of attacks on the systems. I have linked to the, in general, memory safety issues and what are the implications because of those in the slide. So you can look at them later on. I am very terrible at making diagrams, but I try to make one. So it's kind of a very simple visualization of how indirect control transfers happen in programs. And this is like non-architecture specific. Imagine you have a C++ program, and you have a base class which is calling some method. Now, it is usually done as a runtime binding, depending on which derived object you're calling. Your indirect call is placed there. So it's a call which is based on a memory parameter. And if that memory parameter is subject to some corruption, an attacker can go anywhere in the address space. So in this diagram, the blue arrow is basically showing that programmer wanted to go to that particular place in the address space of the program. But if the memory parameter on which this indirect call is happening can be corrupted, then an attacker can go at any instruction granularity in the address space of the program. Similarly, for the return are by definition always based on the memory operands. So whenever you're returning from a function, you're getting a value from the stack, which you would have pushed when you had done the function call. So the idea here is to set up that the problem is memory which is corruptible, and if you're doing certain control flow transfers in the address space, they need some granularity. And it's not like this problem has not been faced by other architectures or people don't know about this issue. There has been a lot of software work which exists in the industry in form of LLVM CFI, SafeStack, and Microsoft's Control Flow Guard, which basically tries, all of these approaches try to use instrumentation, ensure that all the call sites during the compile phase itself or the return sites are checking wherever they are going. And then more recently, x86 came up with control flow enforcement technology, which is basically n-branch instruction for forward control flow and shadow stack for backward control flow. ARM64 also came up with BTI. BTI stands for branch target identifier, which enforces that if you have an indirect branch, you must always land on this landing pad instruction called as BTI. PAC is pointer authentication codes, which tries to mitigate the corruption issues by itself. So that has been one of the mitigation as well. Another hardware mitigation that ARM recently has came up with, guarded control stack, which is pretty much a shadow stack, a protected range in the address space of the program. So the whole idea is that you got to protect the forward flow and the backward flow. For forward flow, you have to make sure that wherever you're landing, there has to be certain granularity on that, and there has to be a specific instruction that CPU is waiting for. And for the backward control flow, you can use the shadow stack for a finer grained return control flow. Okay, so some RISC-V basics. RISC-V is an architecture with, and again, like we can't go into the details of everything RISC-V. I have only put the slides which are, which can help in this presentation. So RISC-V has 32 general purpose registers. They start from X0 to X31. And X0 is basically equivalent to /def/null on Linux. It's a register which is immutable, so you can't change the register. It always is 0. And for program counter, you have PC, which is kind of equivalent to RIP on x86. You might have noticed that there is no stack pointer, there is no link register, so that comes from the calling convention. So RISC-V has this calling convention, which is used by compiler to generate the code. So in terms of calling convention, X1 is the register which is termed as array, meaning return address. So whenever you are making a function call, your return address is always placed into the array so that the function which is called, it can save the return address somewhere. X2 is the stack pointer, which is equivalent to stack pointer on x86. So whenever code is generated, compiler is going to make sure that X2 register is pointing to the stack prepared by operating system for you. And similarly, I'm not going to go through all of them. I'm just going through a bunch of them. T0, T2 is basically temporary registers, which are basically meaning that they don't need to be preserved across calls. Similarly, we have T3 to T6. So the register space is, from calling convention perspective, is segmented into these multiple segments. And compiler basically uses them for generating code. Instructions and addressing in RISC-V. Unlike x86, RISC-V is not that much into variable instructions length. Like on x86, you can have 1-byte instruction and a 16-byte instruction as well. In RISC-V, you can have either 4-byte instruction or a 2-byte instruction. For simplicity, I'm only showing here 4-byte instruction formattings. And what that limits is that how much immediate values you can program into the register, into the instruction itself. So that limits immediate programming to maximum 20-bit. As you can see that the J-type instruction, which is the last one, is the one which is giving you space to program something like 20 bits. But RISC-V has something which is called as AUI PC, which allows you to do a PC relative offset addition in the upper 20 bits of register. So this allows it to basically address plus minus 2 GBs from the program counter. And the other part that I wanted to talk about in the instruction formatting is inputs and outputs. As we earlier saw in the previous slide, we have X0 to X31 registers, 32 registers. And instruction itself provides space to encode what are the source registers, what are the destination registers. So RS1 and RS2, which you can see on screen, are source registers. RD is destination. And they are assigned 5 bits. So you can encode any destination register using those 5 bits between X0 to X32. And same for sources. And depending on which instruction formatting you're using, the source and destination can be different. So I wanted to run you through like a couple of examples here. So as an example here, the first example is AUI PC X6, some immediate value of 20-bit. and then a load from load into X1 register from X6 and some offset. So what this assembly is actually doing is this AUI PC instruction is actually this J-type instruction, the last one in the slide, in which there is some opcode assigned for AUI PC, and RD is programmed to point to X6, and then you have some 20-bit immediate. So what happens by this instruction is, in RD, you add this immediate value on the top 20 bits of current program counter. So you basically have a reach of plus minus 2 GB. So if there is a data section in the program address space, you can reach that through your program counter. And the load is, LD is basically load a double word, SW is store a word, and so on. One thing that I wanted to talk about is JLR, because that's the one which is a control transfer, indirect control transfer instruction on RISC-V. So JLR is actually I-type instruction, in which you are basically saying that I want to go to the address which is present in RS1 register and save the save the subsequent PC program counter in RD register. So in this case, what we are saying is that go to JLR, go to an address pointed to by X8, and whatever is the next PC, save that in X1. So at an ISA level, this is a basic primitive to perform indirect control transfers. Now, coming back to software conventions, and the reason we are talking about software conventions is because if you remember in one of the previous slides, there are software conventions on RISC-V about which registers means what. So if we see that there is only one indirect control transfer instruction on RISC-V, which is JLR, but depending on what are you programming in source register or destination register, they can be called something else. So function call is usually when you're saying that destination is RA register or a T0 register. So these are termed as link registers on RISC-V. So whenever you say that I want to go to an address which is present in register T1, but at the same time save the return address in RA register, so from convention perspective, that's a call. When you really don't want to save any return address, you are actually doing a jump, and in that case, your RD becomes X0, because that was the immutable register. Function returns are basically saying that JLR X0 RA, which means that go to the address which is pointed by RA register, but I really don't want to worry about saving the return address. So that becomes JLR X0 RA. We talked about, so there is one special case which is a indirect jump call, but actually is a direct jump. And that is because RISC-V has this limitation of 20-bit immediate. So you really can't do direct jumps more than plus minus 1 MB. Direct jumps are encoded by I think which one was that? Yeah, direct jumps are, I think, J-type, in which you are basically going doing a direct equivalent of x86. Where was this? So when you're limited by plus minus 1 MB offset, you really can't do direct jump which is farther than this offset. And in that case, what compiler on RISC-V does is it employs this mechanism in which it calculates the offset using AUI PC instruction, which we earlier talked about, and then tries to goes there. But if you look at both of these instructions together, it's actually a direct call. This is not a memory-based operand. What it is doing is, in this first instruction, AUI PC array some offset. So in this example, if you look at, I have provided the offset as well. PC address, which is 70107A. And since it is adding into the upper 20 bits, it is shifting the immediate value by 12 bits and then adding it. It is a signed addition. So it becomes 1007A. And the next instruction is JLR some offset and the register, which becomes 102E0. So this is kind of a plus minus 2 GB direct jump if you look at these two instructions together. So, and this information is going to be useful in the next slides. Because even though this looks like an indirect jump, it is actually a direct jump here because you are calculating the offset statically. All right. So coming to CPU extension for forward control control flow. Yeah, first let's talk about this string ZI CFI LP. So this is the naming convention on RISC-V. ZI specifically means that unprivileged integer. CFI stands for CFI, control flow integrity, and LP is the string for landing pad. So basically the string extension string name itself should be self-explanatory and should present that whether it is part of a privileged ISA spec or unprivileged ISA spec. So that's what it is saying here. What ZI CFI, if a CPU is implementing this extension, what it says is that it enforces all the indirect branches must land on a LPAD instruction, which is equivalent of end branch on x86. With a matching label, except when your RS1 is RA, T0, or T2. So if we look at the previous slide, when compiler uses plus minus 2 GB offsets, as a convention, it uses RA or T0 register. Like existing code, that's what it uses for all these kind of more than 1 MB offset direct calls. So that kind of frees up the compiler from using array for generating those kind of direct calls, and at the same time does not require a landing pad at the target. We talked about matching label. What matching label means that is this new instruction LPAD is designed so that it has, you can program an immediate value as part of the instruction itself. And at the call site, you set up some label value in a register, which according to this ISA extension must be T2 register, which is by software convention, it was X7. So when CPU is not able to match the contents of T2 with the label programmed in the LPAD instruction, then it's gonna raise a fault. The fault is basically a software check exception on RISC-V, and the TVAL is here equivalent of something error code on x86. So it's like extra information telling CPU, telling software that why did this software check exception happen. Here is some example. So this is a call site in which you are setting some label value in T2 register and performing an indirect jump. And at the target, you must have a label which must have a label value is equal to 1. And then your rest of the function body starts. Here is the second example, which is using T2, which is exempt from any landing pad. So here you are placing some PC relative offset, and then you are doing a jump there. Now, no label is expected at this in this flow. ZI CFI SS is protecting the return flow using shadow stack. Because shadow stack can be anywhere in the address space, and it can be discontiguous because there can be multiple threads in a single address space. You need a way of telling CPU that this is a shadow stack, which cannot be tampered with regular store instructions. So there is a new page table bit to in the ISA extension to make sure that the shadow stack is not writable. But it can be writable using only shadow stack instructions, which are mentioned here as SS push or SS ammo swap. Ammo swaps basically means that atomically swapping a value on the shadow stack. SS pop check is instruction which is going to pop a value from the shadow stack and match it with one of the RS1 register, and if they don't match, it's going to fault. SS RDP is equivalent to read the current shadow stack pointer, and yeah, the extension itself introduces a new register in the ISA, which is called as SSP register, shadow stack pointer. So that's on top of the existing GPRs. Now, when you have a program compiled with these ZI, CFI, SS, and LP as well, your functions will have landing pad at the start with a label value and SS push array, because whoever called it must have made sure that return address is placed in array. And in the epilogue, before returning, what your function should be doing is SS pop check array. It must have loaded array from the regular stack earlier in this step. And SS pop check is basically going to pop from the shadow stack, match that contents with array. If they don't match, it's going to raise a software check exception with the error code of 3. If it doesn't fault, then you can basically do a return. There are additional things that I wanted to talk about with respect to shadow stack. So left side is assume your program was already using shadow stack, and in general, only shadow stack instructions are allowed to access shadow stack. So SS push, SS pop check, or SS ammo swap. So the blue lines are representing the valid accesses, and the red lines are representing invalid accesses. So what it means is that when your program is running, any SS push or SS pop check or SS ammo swap kind of accesses that are happening, they must happen only on shadow stack. If they happen on any read-write memory or read-write execute memory or even execute memory, that will result into access fault. Access fault is kind of a fatal fault on RISC-V. So operating system basically takes drastic measures for the program which is resulting into access faults. Because there is no need for these instructions to work on a read-write or read-write execute or execute memory. So that's the inbuilt into the ISA that these will result into access faults, so that nobody can pivot into non-shadow stack memory. Similarly, we don't want regular store instructions, which is basically SW here, to write into shadow stack. So all these instructions attempting to write into shadow stack type of memory is going to result into access fault. But there is an interesting case here. There are two interesting cases here. One is how do you do cow? Because when we're running programs, you are doing forking and cloning all the time. And in that case, your address space is cloned. And how do you perform cow on shadow stack memory? And by default, what kernel does is it marks the pages read-only. And in this case, shadow stack range will also be marked as read-only. What happens when the subsequent SS push or SS pop check or SS ammo swap happens on that range in the new clone task? So for that, what ISA does is, if there is a SS push, SS pop check, or SS ammo swap operation, and it is dealing with a read-only memory, all it does is it raises a store fault, because it assumes that this condition can only be done by a fork or a clone. And operating system already knows what VMA this was, and it can program the right permission bits and resume the instruction. And loads are allowed on the shadow stack because it is going to be useful for stack tracing and things like that. I'm going to go through this one fast, but we can talk about this one later on as well after the talk, because I think we are running out of time. SS ammo swap is is designed for asynchronous software. And what I mean by that is you have signal handling in kernel in which your control flow gets hijacked at some point of time and then it goes somewhere else. Similarly, in high-level languages like Rust and Go, you have concept of async, await, green threads, in which you are basically constantly switching the stack for these kind of asynchronous flows. And quite often, attackers use these kind of asynchronous flows to do stack pivoting and eventually perform control flow hijacking. And if shadow stack were to be enabled for these flows, shadow stack will also have to be switched. And the way to switch shadow stack should be not just switching a stack pointer, shadow stack pointer, but some way of securely doing that. And there is a concept that is basically storing certain kind of tokens on the shadow stack, which you can verify whenever you are switching. So as long as runtimes has that mechanism of storing the tokens and validating those tokens before actually switching to the shadow stack, it provides extra security assurance. SS Armor Swap basically helps with that flow by storing and validating those tokens in an atomic way on the shadow stack so that there are no concurrency issues in terms of this validation flow. Okay, key ISA distinctions that RISC-V has is unlike other architectures where your return address is pushed onto the shadow stack as part of the call instruction, that's not what RISC-V does. In case of RISC-V, you have specific something, SS push instruction, so compiler emits that code in your function prolog. What it gives to the software workloads is that all the leaf functions, which are not spilling return addresses, they don't have to store that address somewhere in the shadow stack. So, C++ workloads which have lots of getters and setters, and there are lots of leaf functions, you can get some performance back from there. Shadow stack, because there is no implicit push and pop of the as part of call and return, it allows mixing of the DSOs in the address space. So if a DSO does not have shadow stack compiled in it, it's not going to result into any issues. You can easily mix and match that. Landing pad is basically, landing pad key ISA distinction is that it allows fine-grained assistance. So label value is programmed into the LPAD instruction, which basically means that you don't have a branchy code in your prolog where you are checking the label value of where you're coming from. Okay. This is the status of the RISC-V CFI user mode enabling. We have posted V3 patches on the kernel mailing list, which, and thanks to a lot of existing work from Rick on the x86 side, that we have been able to use that work to enable these patches. These patches basically do feature discovery and activation. One part which is interesting is that as we are developing this, we have found that there are lots of common flows between ARM64 shadow stack, x86, and even RISC-V. So one attempt is trying to get to do as much as Arch agnostic code for these things. And as part of that, we have at least settled on some generic PRCTL to enable these features on the binaries. In terms of testing, what we have done is we have built up build root, rootfs using shadow stack and landing pad and able to boot to the shell. There is a demo. I don't know if you'll get to see that. Yes, so RISC-V kernel control flow integrity. We have posted RFC patches for this to LKML. For forward CFI, it's as simple as you have to compile the kernel with this compiler flag. And for backward CFI, we are hooking on something called as config shadow call stack, which exists in kernel today for ARM64 and even for RISC-V. What this config does is it prepares a software shadow stack, which is writable. And there is a compiler instrumentation in Clang, I think, which stores the return addresses into this software shadow stack as part of the prologue and epilogue, it pops it up. So we are basically hooking into that existing flow to enable hardware-based shadow stack on RISC-V, and it works pretty good. Within like 12 patches, we are able to enable this KCFI for RISC-V kernel. I did some label collision analysis as well, that and these labels are calculated over as the MD5 hash of the function signatures, just to check how much label loss we see as we reduce the number of bits to store the label. Because as of now, as we talked, that RISC-V has only 20-bit immediates available. So the label that you can program is 20-bit. And this is like a very rough analysis that I have done. I used LLVM dump AST feature to grab the function signatures and then calculated MD5 hashes over them. This is a small cute graph that I was able to make. What it means, these percentage means is that, so here is the unique prototypes. And between the unique hashes, when we truncated it to 20-bit, how many of them still remained unique? So like for C++ sources in the file, it was a 12% loss. For C files, it was 3%. And so on for all of them. I have 2 different bullets for CPP and C because I was having some issues when I was doing the AST dump, because for CPP, it was all coming out mangled. So I basically tried to separate them apart. Average, we compiled spec 2006 binaries. Average code size growth that we saw due to the feature was 1.91%. And there is still scope of optimizations to further reduce this growth. Average indirect gadget reduction is something which is existing metric used to calculate how many gadgets indirect gadgets have you reduced in the program address space. So we calculated that came out to be 99.43%, but that exists for other KCFI or other CFI schemes as well. There are more details about these numbers in the spreadsheet, which I have linked over here. These are the CFI repos that I have. ISA specification is over here. There's a compiler support, which we are getting a lot of help from Sci5. QEMU support, kernel patches for user CFI, and RFC patches for kernel CFI. OK, do you want to see a demo? Otherwise, we can take questions and answers.
We're over time.
Yeah. Yeah. Yeah, talk to me if you're interested in discussing anything about this. Thank you.
Hello. So I'm wondering, how can you encode landing pad label and shadow stack while writing C code, since I'm interested in using these techniques, writing microcontrollers code based on RISC-V.
What was your question?
How do you, since you show some assembly code for using landing pad and shadow stack, but I'm interested in writing the code in C.
Mm-hmm.
So do you have any?
Yeah, so when you, like the compiler support that I showed, when you use that compiler to compile your C program, it will automatically generate that code for your C function. And
for each C functions?
For each C function, yes.
I see, thank you.
It will do that.
Are you generating the landing pad labels in the compiler as a function of the signature of the function, or are you doing it in the linker basically like it's a one-up count? It seems like you can do it either way. Using the signature of the function itself is
Hey, check 1, 2. Hey. Well, it is going to the mixer, I see. So.
Well, it is, yeah. I had a room full of people who can verify me.
No, I believe you, 100%. Yeah.
Oh. There you go.
So.
That one's working again.
Yeah.
So I wouldn't be surprised if this is it right here. Oh, now it's working. Oh, there you go. Interesting.
Hey. Check 1, 2.
Fail points on these things are inside.
Hey. Check 1, 2.
So it's very possible that it's not, the connections become loose inside. So Kevin will mark that and have it tested out at the shop.
Hey. Check. Hey.
Go grab some lunch. It's really good.
Hey, check. Two.
Hello, everyone. My name is Zahra. I work for Microsoft on various systems and security projects. And in this talk, I want to discuss some of the ways that we can use large language models for improving kernel bug discovery.
try now.
Hello. Hello, everyone. Good afternoon. I am Tara Gopinath, and I'm here to talk on Linux virtualization-based security. I work at Microsoft, and for the last 2 years, I've been leading this team of very smart engineers who are trying to prototype, productize, develop this solution. And with me, I have Anna, and I'll let Anna introduce herself.
Hi, everyone. My name is Anna Trikalinu. I've been with Microsoft for about 2 years, working on the thing that we're going to present today. And before that, I was with Intel for about 7 years, working on confidential computing, side channels, and so on.
OK, so let's get started. So this is what we have in agenda today. We'll start with an introduction and a brief motivation on why we decided to pursue this project. And then we go into a bit of background on Hyper-V as the hypervisor. We talk about the threat model in Linux virtualization-based security. And then we briefly look at how this all ties in with Secure Boot. And then we go on and explore the two initial features that we wanted to target with the solution. One is protecting the guest memory, and the other one is protecting guest registers, or kernel registers. Finally, we have a demo, and then we conclude with and we talk a bit on what we want to do next. So let's start with the motivation. So when we started this, what the thought process behind this was, like, Linux kernel is growing. And as it grows, there are more and more vulnerabilities introduced into it. Every month or every other month, we hear about exploits and threats and things like that. So our goal here is to actually harden the existing kernel protections and back it up using hypervisors, so that even if a kernel is tampered with, even if there is a malicious attacker that has gained entry into the kernel, these protections cannot be turned off. And as an extension of this goal, we also want to ensure that some of the key system assets, like, let's say, keys, passwords, critical kernel data structures, they remain untampered even if there is a malicious attacker in the kernel. And then, OK, so this solution is called Linux virtualization-based security. It is derived and inspired from Windows VBS. Windows has this virtualization-based security running for a while now. And the basic premise here is what we use hypervisor and hardware virtualization support to protect kernel. We say guest OS because primarily we are been looking at guest kernels to start with, but theoretically it can be even the host kernel. And one of the basic principles behind our architecture is we want this to be an open source architecture. What that means is we want it to be hardware agnostic. Currently, we have this solution working with both AMD and Intel x64 architecture. We want this to be hypervisor agnostic. We again have this working with, or parts of this working with Hyper-V and KVM. I have Mikhail here, so he is working on the KVM part of things, and he has already posted some RFC patches under the umbrella of hypervisor enforced kernel integrity HECI. And this presentation itself will focus on the Hyper-V implementation. And even the Hyper-V parts of things that we want to introduce into Linux kernel and the secure OS that you will hear about in a minute, we are looking at upstreaming all that support. And we already have the code out there in the GitHub repo. So now, as we get into architecture, let's quickly look at how a Hyper-V based system looks like today without any support for LVBS. There is hardware. There is Hyper-V running at ring -1. And then the system itself can be partitioned. There is a root partition and multiple guest partitions. And there is kernel running at ring 0 in each of these partitions, and there is user space at ring 3. And for LVBS, we use a Hyper-V mechanism or Hyper-V feature known as Virtual Secure Mode, VSM. And once we turn on VSM, this is how the system looks like. Again, there is hardware. There is Hyper-V running at ring 1. System is partitioned into root and multiple guest partitions. And each of these partitions, now we have separate execution environments. They are called virtual trust levels. theoretically, each of these partitions can be subdivided into 16 VTLs. Hyper-V has support for it, but for the purpose of this talk and for the purpose of LVBS, we only have 2. There is VTL 0, where the regular guest OS runs, and then there is VTL 1, which is where we want to introduce a secure OS in order to provide the protections that we want with LVBS. Also to be noted is the fact that higher is the VTL, more privilege the VTL has, which means VTL 0, the guest OS, will have the least privilege in the system. We'll quickly look at a few VSM features. We can't go into details of all this, so there is a link there if someone is interested to read more on what VSM is. So one of the basic features, it offers virtual processor state isolation, which means it allows each of the VTL to define its own set of CPU register and have its own virtual processor context. Also, it allows for memory hierarchy and protection, memory access hierarchy and protection, which means that each VTL can have its own guest physical memory access protections, but also a higher VTL can impose memory restrictions on a lower VTL. For example, if I have VTL 0 that goes in and says a piece of memory should be read-write, and I have VTL 1 that goes and says that the same piece of memory can only be read-only, the permission or the protection that is set by VTL 1 takes precedence here. And finally, it allows for virtual interrupt and intercept handling. Each VTL has its own interrupt subsystem, and always a higher VTL takes precedence over a lower VTL. If there is an event in a higher VTL, Hyper-V enforces that the CPU is switched over to the higher VTL, which means that a higher VTL can process the interrupts without interference from the lower VTL. And the jump back has always to be initiated by the higher VTL. So now we look at the software architecture. Again, there is hardware and Hyper-V. And this is a guest partition that we are looking at. It is divided into VTL 0 and VTL 1. VTL 0 has guest kernel and the user space running. And inside the guest kernel, we have a VSM boot driver that loads everything in VTL 1. And we talk about that a bit more on why we decided to do that. And then there is a bunch of hypervisor agnostic layers for memory protection and exception handling and things like that. And this is how we are building this to ensure that the solution is hypervisor agnostic. And then there is VSM driver itself, which kind of takes the request from this hypervisor agnostic layer and passes it on to VTL 1. On the VTL 1, there is a very minimal bootloader running in the kernel mode, which allows you to load the secure kernel. And in the secure kernel, which is a minimal Linux kernel today, there is an interrupt and intercept handler. There is a VSM driver and a memory protection interface. And there can be a user interface which can be extended to enable trustlets and secure apps, but that is not implemented today. So a quick look. So we want this to be a self-contained solution. And I talked about the VSM boot driver, which loads the secure OS in VTL 1. And the reason is we did have a lot of design discussions on which component should launch and set up VTL 1 secure kernel. The options we had here were, one was hypervisor, which would mean that we tightly couple this, which it kind of becomes that the hypervisor and kernel becomes coupled together in this case, and which we didn't want. The second option was the bootloader itself, which means use the UEFI bootloader that loads the guest OS today and ask it to load the secure OS as well, which is probably not scalable as we want to move from one guest OS to the other guest OS. And finally, we landed on the solution where we said that we can trust probably the kernel till the init process, the first user process runs because of secure boot, and we will let kernel load the secure OS in VTL 1. With that, I hand it over to Anna to talk on threat model and the rest of the slides.
Okay, so we said that we selected the guest kernel to be responsible for booting VTL 1. So the guest OS that we are trying to protect is going to be responsible for booting this secure OS to apply protections to it, which kind of doesn't make sense, because if the guest kernel is malicious, then how do we trust it to boot this secure OS to apply these protections? It will just skip it, right? Well, Not exactly. So our goal is to protect the kernel from a user space attacker exploiting a kernel vulnerability. But we assume that the kernel is benign. We do not start with a malicious kernel. We assume that initially the kernel comes from a trusted source, so that can be canonical, for example, and that the integrity of that kernel is verified. So both the authenticity and integrity security promises are guaranteed by secure boot. So with that in mind, we can make sure that initially when the guest kernel starts to boot, it's something that we trust. However, we do have the premise that even though this is a trusted kernel initially, this kernel is vulnerable. It can either have an unpatched CVE or it just have a 0-day that we just don't know of yet. And that's very plausible because there are many new kernel vulnerabilities that come every year. Okay, so we trust the guest kernel initially until the very first unverified user process starts running. And that is the init process for us. So up until this point, the guest kernel starts to boot. It's doing the initial setup, initializing memory and everything. And this is where we added our functionality. So this is where we verify everything that runs in VTL1, so the secure kernel and the mini bootloader that we have. After this is verified, we boot VTL1, we apply the memory protections that are immutable, meaning that if the guest kernel tries to change those protections afterwards, that will fail. We also lock the control registers, and after that, and after all these protections have been applied, then we do the init process. And after that point, we assume that the kernel is not trusted and couldn't be exploited. That could be, for example, because we have an unverified user application just exploiting a kernel vulnerability and then granting kernel privileges to the attacker. Okay, so we semi-trust the guest kernel, at least the trust is temporal, but we do have full trust in the hypervisor, the host OS, and the hardware. So all of those are inside the TCB. However, even though our architecture, LVBS architecture, trusts the hypervisor, our security goal is orthogonal with and complementary to confidential computing. So our goal with LVBS is to protect the guest kernel from itself, essentially. And the goal with confidential computing is that we want to protect the guest from either a malicious hypervisor, malicious host OS, or just an admin, or someone that just walks into the data center and just starts to mess things around. So those are slightly different. And right now, our solution does not work with confidential computing. However, it is possible to happen, and we actually have it as a future work. So in that case, instead of using the hypervisor to apply the memory protections, we are going to use the hardware and firmware extensions that are supported as part of new confidential computing hardware. And we're also going to use the paravisor for doing the register pinning. Okay, so now let's talk a little bit about secure boot. On the figure that you see below, you see up until, initially, this is how the secure boot works. We're just extended that chain of trust. So initially, UEFI firmware is the one that is verifying the integrity of the shim. If we have a Linux kernel booting, then the shim is the one that is using the canonical key to verify the integrity of the bootloader, such as grub, and verify the integrity of the VTL0 guest kernel. So what we did is that we extended that, and we are saying that now the guest kernel, before the init process starts, so while the guest kernel is still trusted, it will also verify the integrity of the secure kernel, so everything that runs in VTL1. And For that, we used just standard SHA-256 with RSA and PKS7 signature. The one slight thing that I guess it's important is that, okay, what is the key that we are going to use in order to verify VTL1? For our environment, which is a dev environment, we've added one key to the VTL0 system trusted keys. So when we are compiling a VTL0 kernel, we use a config register and we say, okay, this is our public key. Please use that in order to verify the integrity of VTL1. This is for dev purposes. However, if or when, hopefully, our changes are accepted in mainline, we can just reuse the canonical key that is already part of the system trusted key rings. And we can use that canonical key to verify the integrity of VTL1. So the figure will not change. It's just that instead of using that VTL1 purple key, we'll just use the orange one. This is the way that we generated the signatures for the secure kernel and the bootloader binaries. We just used a standard script that is part of the kernel. And then we added the signature files as part of the VTL0 initRMFS. We added the certificate, as I said, to using that config register. Before the VTL1 boots, VSM boot driver reads those signatures and verifies that they are indeed signed with that, that they are signed with the private key of that key pair. Okay, so now we know that what we've loaded in VTL1 is trusted. Now let's talk about what is the interface between VTL0 and VTL1. One thing to note is that we want the VM to run on VTL0, which is the guest, 99% of the time. We want the guest to run its own workload instead of to steal cycles from that VM in order to do those security protections. So that's why we mostly say about transitions from VTL0 to VTL1. And in order to do those transitions, there are 3 ways to do that. One is an explicit VTL call, which is just a special hypercall that is done. So VTL0 does a VTL call, and that transitions the VP from VTL0 to VTL1. There are currently 4 opcodes that we have defined for doing that VTL call, and we use 2 opcodes for booting VTL1, one that enables VTL1 for the secondary processors, and the other opcode for booting those secondary processors in VTL1. And then we have 2 more opcodes that are used for applying protections, one to protect memory and the other one to log control registers. So I'm going to talk about those 2 later on in the presentation. The important thing to note here is that 3 out of those 4 VTL call opcodes can only be done before the init. So we make sure that if there is a VTL call with the 3 out of the 4 VTL calls after the init process starts, it's not going to do anything. The one that we do allow is the protect memory. However, any memory that has been protected prior to the init process, the protection is immutable, meaning that if the kernel after the init process starts, so a potentially malicious kernel tries to change the protections for a piece of memory that has been set with a set of permissions, and this is marked as immutable, then the latter VTL call which will change the permissions will not succeed. Okay, the second way to transition to VTL1 is through secure interrupt. As Tara said, the VTLs are hierarchical, meaning that if there is an interrupt pending for a higher VTL, then the VP will transition to that. And one thing is that one main or big source of interrupt is the timers that just does periodic interrupts. However, we disable timers in VTL1 while VP is in VTL0, and that is in order to reduce jitter. And thirdly, there is the secure intercept. So whenever VTL0 violates one of the protections that VTL1 has set, then the VP that triggered that fault will enter VTL1. Okay, so now let's talk about memory protections. In order to do that, we have used the memory protection framework that you saw in the earlier slide that is introduced by Heki. This is the RFC for anyone that is interested in that. So I'm just going to briefly talk about it here. But if you want to know more information, there's a bunch of it. I will highly recommend that you go see this RFC. So as I said, this component is common between Hyper-V and KVM. And what Heki, or memory protection, does initially is that it allocates permission counters for each 4 KB page in the guest. So for example, if the kernel has large pages, then the VTL0 will allocate multiple permissions in order to represent that page. We also need counters instead of just 1 bit to say if it's read or write, because we can have multiple mappings. So multiple guest virtual addresses can map to the same guest physical address. So we want to capture, so the permissions that are applied in the EPT is going to be the union of those permissions. So if there's one mapping that says, I want to read that piece of memory, and then there is another page within VTL0 that says, I want to read-write this memory, we have to, the EPT permissions need to be the union, so both read and write. Otherwise, we're going to break the software. The permissions are captured as read, write, and then execute is divided into user execute and kernel execute. And in order to do that, we utilize a hardware feature that is called MBEC. And then finally, Heki will get a capture of what is the guest page table permissions initially, and then it will track how those permissions change over time. So if we want to map this into our VTL model, we have a figure of how this will look like. So initially, VTL0 will allocate and update those permissions, and then before the init process starts, VTL0 would do a single VTL call that says, here's the memory that I want to protect, here are the permissions that I want, and please make them immutable. VTL1 will receive that request. It will store the memory ranges that are mapped as immutable, and then it will do a hypercall to Hyper-V that says, please apply those permissions in the EPT. Hyper-V will do it, and then we will return to VTL1, and then later on in VTL0. And again, all of this happens before the init process starts and while the guest kernel is trusted. This is a look of the permissions that we have set. So the read-only data section is marked as read-only. The text section, which is where the code for the kernel lives, is marked as read and kernel execute. VTL1 memory is marked as read-only, and everything else is marked as read-write and user execute. Again, this is the view of the memory as from the perspective of the VTL0 guest kernel. And if you want to look at the comparison, the default permissions, so without LVBS, the default permissions that the Hyper-V will apply is everything. So read, write, kernel execute, and user execute. So this is, I think, a big improvement that we have with LVBS. If after we apply the protections, there is an EPT access violation, then a memory intercept is injected to VTL1, which raises a general protection fault in VTL0. And as I said, if there's a subsequent request for changing permissions on a region that is already protected and marked as immutable, then that request is ignored, and we have future work to add some bookkeeping and maybe report that request that maybe is suspicious. Something is suspicious running in guest kernel. Okay, so now let's talk about register pinning. Hyper-V supports intercepting access to a number of registers, and I have the full list on the right side here. I hope it's legible, but there are quite a few. And we have divided this set into, divided those registers into two sets. The first set is the one that you see on the table on the first row. So any writes to those registers will get blocked and will raise a GP fault in VTL0. The second set, which is the second row in the table, any writes to any of those registers, we check whether the new value that is being written is the same as the one that was there in pre-init, so while we trusted the guest kernel. Otherwise, the write gets blocked and we raise a GP fault. The reason why we have this second list of registers is that those registers lose their value when let's say the VM goes into suspend. So when the VP loses power and the VM goes into sleep mode, then hypervisor sets those registers to 0. This is emulating what the real hardware would do if that guest was running on in bare metal instead of the Hyper-V. So those registers are set to 0, and then when the VM comes up, the VM is responsible for setting those values back. So we want to allow the writes to those registers, but we want to make sure that they are set to the same value as they were when we were trusting the guest kernel. And here is the flow of doing the register, locking the CRs. VTL0 is responsible for setting the security policy and the mask for VTL0, for the control registers. And then for each VP that is present in the guest kernel, each VP does a VTL call that says, please lock the registers, and here's the mask that I want to apply. VTL1 saves the register value that was there that is used as the ground truth for subsequent writes. And then after that, it's doing a hypercall to Hyper-V that says, please lock them. The Hyper-V applies the locks and sets the masks, and then we have, it returns, every VP is returning to VTL0. If there is a subsequent write request to one of those registers that is monitored, then an intercept is injected to VTL1. Okay, so let's talk about a little bit of exception handling. So I just said if there is, if the VTL0 tries to access a register that is locked, or if VTL0 tries to access a piece of memory that has applied some protections, and it's violating the permissions that were set, then an exception is raised. In that case, VTL1 injects a general protection fault to VTL0 and returns the control back to VTL0. Then that VTL0 will cause the thread to be killed, and depending on the configuration, it could cause a kernel panic as well. And here is the flow. So assuming that the attacker, after the init process and when the attacker could be compromised, if the attacker tries to write in, let's say, and modify a read-only memory, then the hardware will walk the EPT tables. It will see that the permissions do not allow the write, and then it will trigger a violation in the hypervisor. The hypervisor will cause an intercept in VTL1, which will say, oh, this happened, this is not allowed, and then that will inject a GP fault in VTL0, which in turn is going to kill the thread and panic. And with that, Tara is going to show pretty cool demo of our technology working.
I will try. Let's see if this works. Okay, so I will play the demo and I will talk through it. That's the plan, because I don't think the volume will come out pretty well if we just let this run. Mute the volume. Okay, so what we are trying to do here is to show that how we protect some of the system registers that Anna talked about using LVBS. So the demo here is we use the IDTR register for this demo. It is the interrupt descriptor table register, and it holds the base address and limit for IDT table. IDT table itself contains information on interrupt handlers and exception handlers and things like that. And it resides in the read-only memory of the kernel. So the idea here is that even if it is read-only, let's say all the protections are applied and the IDT table is read-only. If a malicious attacker gains entry into the kernel, they can actually change the base of the IDT in IDTR. They can make the IDTR point to a different IDT and it can be and you can have spurious entries in that IDTR. Attacker can do whatever they want to do with that. So in this demo, first we run this on a system without LVBS enabled and see what happens, and we can show that the attack could be successful. And then we run it with LVBS, and we show that LVBS will raise the general protection fault that Anna talked about, and which will eventually lead to the system crash and things like that. As we play this, is that legible? Okay, I'm assuming so. Okay. What happened? Okay, so this is a test. It's a kernel module at this stage. And the test itself, the test case itself is quite simple here. What we try to do, I'll skip forward. And what we try to do is we run this on 5 CPUs in parallel. And before the test, I kind of go and create a new IDT table. I just copy it from the existing IDT table, but it's so that it's in a new location and things like that. And I'm not malicious at this point, so I don't create any spurious entries or anything like that. And then I spawn this corrupt IDTR test function on these 5 CPUs. And inside this function, what I do is I go and store the current base address, the IDT base address from the IDTR register. Okay, I'm sorry. Let us just talk about it. Yeah. So I store the current IDT base address, and I attempt to load the IDTR with the new IDT base address, and then at the end I kind of check if I read back the IDTR register, and then we say that if there's a change, basically, if there's a new IDT address in the IDTR which doesn't match with the original IDT address, the hack was successful. Let's run this. And so yeah, so this is a system without VSM or LVBS enabled. And this is a module, so I am just inserting the module at this point. And it ran through, and let's look at the D message. Okay, I don't know if you can you see that? Can you see those red lines? Okay, I don't know. Okay, so what it says is the test ran on 5 CPUs, CPU 17, 18, 21, 5, and 23, and all of them, this hack was successful, which means that the base address in IDTR was changed. It was originally X, and now it is Y. I managed to put in my new IDT address in there, and the hack was successful. And now let's go and run this on a system with LVBS enabled. Let's see. Okay, so here I have LVBS enabled, which means you will see prints for saying that, okay, some memory protections have been applied, some of the registers have been successfully locked down, and things like that. And in the system, let's try running. And let's try running the test. Yeah, it should come up in a second. There you go. The system actually crashed here. What you see on the left is the crash dump, basically. So what happened here was, again, the test ran on 5 random CPUs in the system. We tried to corrupt the IDTR register. It got intercepted at VTL1, and VTL1 injected a GP fault in VTL0, and VTL0 raised a oops on that, and the system has actually panic on oops set, so which means it went and system died and it crashed. And that is the end of the demo. And I think we have like one slide, and we can talk a little bit on
put it into present.
Future work that we are planning to do with this technology. So one of the things what we want to implement here, and which is in progress actually, is module authentication, where we say that, okay, we put all these protections in the kernel memory, but kernel has a bunch of features which actually wants to change some of these protections, for example, to load modules. There are other features also like kexec, ftrace. So we need to tackle all of that, but initially we are tackling module authentication. So the point here is, if we want to change the memory permissions that are set up initially at kernel boot, like Anna talked about, we should authenticate those changes before we allow those new permissions to be set. And for that, the first feature that we're targeting is module authentication. The other thing we are attempting to do is to extend and implement some secure user interfaces in the secure OS running, in the secure kernel running in VTL1, so that we can support trustlets and secure apps. And finally, like Anna mentioned, we are trying to see and intersect and integrate this with confidential VMs and confidential computing. With that, okay, so this is where we have hosted all the code that we have today, and we are planning to upstream most of this. And that brings us to end of this presentation.
I also want to mention that yesterday we had a presentation in OSS that we went into a lot more details on how we boot VTL1, which included what does the bootloader does, what does the VTL1 does in order to boot both the primary processor and the secondary processors. So if you're interested in that, please check it out.
Yeah, it talks a little bit more on how we decided to choose minimal Linux kernel as the secure OS and things like that. So yes.
Any questions?
I'm sure you've been asked this question many times, but you already said that this work and confidential compute are orthogonal. But like we saw in the morning presentation thing about SVSM, right? The kind of functionality that this thing is providing is kind of similar to SVSM as well. Like, you know, SVSM also can provide virtual TPM and things like that. And I think one of the functionality that VSM provides is VTPM and these kind of secure functionalities. So don't you think it will be like more beneficial if there is a single module which is serving for confidential compute needs as well and the needs of protecting the guest kernel as well?
Yeah, so right now, in order to provide, for example, virtual TPM capabilities or what we call the paravisor for confidential computing. So if the guest is not aware of confidential computing, there is the paravisor that helps to alleviate that pain or before all the changes are implemented in the guest. But now it seems like the paravisor is here to stay. And one of them is because of virtual TPM. So right now, this is running on a different VTL level. there has been a lot of discussion whether we should merge it or not. And there are pros and cons in each option that we take. The main case for having them separate is because the paravisor, the purpose of the paravisor that is doing this is mostly seen as an extension of the hypervisor that we don't trust. And it's supposed to be OS agnostic, meaning guest OS agnostic, as opposed to this, which is highly coupled with the OS that you have running in VTL0. So Windows have its own very different version of VTL1. Linux will have this version or some version of that. So that was just one option towards having them separate. But there are benefits of having them together, I agree. So we'll see.
Yeah, we can chat later.
I will just add on to that whatever Anna said, that for example, there are features that VSM offers, let's say the control register or the register protection, right? That today, if you want to do with either paravisor or confidential computing, we need hardware extensions for it. It is available because Hyper-V allows you to intercept and interject and raise those exceptions in case of violations. Hyper-V has that capability today. Whereas those things, if you want to support with CVMs, we need hardware support for it.
Right, but SVSM is running on x86 hardware, right? And this is also x86 hardware. It is interacting with a VMM which is below it. It
is, but it doesn't have support to raise an exception. It doesn't have that support, or someone has to bring in that support.
And that was my primary question. Right now, it does not have support. All you have to add is code to invoke those hypercalls. Then it can do that. So I was basically thinking that to maintain two different kind of parallel VTLs, one for confidential compute, one for this, does it even make sense?
I agree. I agree that they could. Look, you can implement it either way. Both of them are going to work. If it's one, then it's better because you only have one additional kernel that you have to worry about, right?
Yeah, that's just a suggestion. It might, it might lead to, better adoption rate as well because you have now two use cases for one piece of software.
Yeah. I don't have strong opinions either way.
Hello. First, great work. I work for Azure, so I'm really excited to see this. Definitely going to look it up and ask questions soon. Question is, do you support kernel modules at all, or is it like a no-go here?
Right now with this, no, but we are adding it. So we are working towards adding it. And
okay, cool.
That is our very next step, basically, to add kernel module support.
Okay, also BPF, I assume, same
no,
or no?
BPF is lower in that list.
Okay,
we want to go.
Keep it away.
Yeah.
And the other question I had is if you have two virtual addresses kind of mapping to the same physical page, how is that handled? So you have two different virtual addresses. So I assume you should be using the virtual addresses to map the permissions. So could you use a different mapping to that very same page which you block to circumvent the protection? Does it make sense?
So the permissions, we set them at the EPT, so the extended page tables that are handled by the hypervisor. Okay. What I talked about earlier is having two mappings into the same GPA. This is the first level page tables which are inside the VM. Okay. So at the end of the day, if there is one mapping that says read and the other mapping that says read write in the first level page tables, and both are valid, then the EPT, in order to allow both transactions from, let's say, both applications, it has to be the union of it.
Okay, so get the most inclusive. Okay, and the last question, that's me not knowing enough about virtual machines, but does FISMAP is a concern? I think FISMAP is not available in virtual machines, right? Physical mapping of doesn't ring a bell. Oh, doesn't matter.
Physical mapping of memory?
Yeah, because the kernel has mapping of the physically loaded memory pages, so you can basically access all that is currently in the RAM. You can access from a specific mapping inside Linux kernel, but I'm not sure if it's available inside VMs or not.
All of them are mapped as
Okay.
virtual memory. When it comes to the VM, it only sees just physical memory. It doesn't see the actual physical RAM that you have in the system.
Yeah.
And the problem exists, and that's what they solve.
Yeah, yeah. Okay, cool. Thank you.
Thank you.
Hi, I had a question about the register list that you had on like slide 16 for register pinning. You list a bunch of CR0 and CR4 things. I was kind of expecting like SMAP and SMEP to be in that list. Do you pin those, or what's the
I didn't. Can you repeat your question, please?
I'm wondering if the SMAP and SMEP bits in
CR4, yes, they are protected.
Okay,
yes.
cool. I just didn't see the list.
Oh yeah, I think we missed it. Yeah,
Okay.
so the SMAP and SMEP are in the list of bits that is protected.
I suspected they would be. I was just like,
yeah.
Okay, cool.
Yeah.
That's CR4, yes.
Sorry,
yes.
that's
I
my
think
bad.
we just missed it. Yeah, so yeah, it is protected, yes.
I think we are out of time, but one more question.
Because Keys brought the question of SMEP and SMAP, I remember like Windows-based deployments of VSM, they use these x86 features like page table protection using HLAT, or to prevent any shellcode execution in user mode with using this MBAC feature. I don't think they exist in like Linux mainline yet. Is that like still on the, are there any patches in the mainline to support those features?
So we are using MBAC in our solution, where we say that only kernel text has kernel execute permissions. And other like user mode or the other guest pages or other guest memory gets only user mode execute permission. They don't get kernel execute permission.
But when you have KVM as the hypervisor?
What's that?
When, let's say, you have KVM as the hypervisor.
When we have KVM, that is what Mikhail is working on, to implement Heki, where he has actually, as part of Heki, he has introduced MBAC support into KVM.
Yeah. And for HLAT, I know that it was also part of our to-do list to have support for it.
Yeah. Yeah.
Okay. Thank you.
Thank you.
Hello? Ready to go? Or yep. Hi, everybody. My name is Terrell, and I've got my colleague Fred here. And today we're going to mix it up a little bit of kernel for the people in the audience that like kernels, and also a little bit of data science and analytics for those that like that. The title, the work today we're going to talk about is called Provenance Aware Integrity Monitoring with Linux Security Identifiers. This work was done, Fred and myself, in collaboration with some great folks at Penn State University, Aditya, Raul, Eddie, and Trent. But first, a little bit about us. Fred and I have actually worked for IBM Research for about 8 years. We work on some open source projects. We're maintainers and contributors to two projects in particular. One is called SysFlow, and the other is called Falco Security. Falco Security is a runtime analytics tool, and so we actually use some of Falco inside of the SysFlow project. We're sort of passionate about program understanding, so understanding what a process is doing, and sort of trying to apply semantics to that to be able to better understand that, so that we can make better decisions and understand security alerts and things like that, ultimately making the security analyst's job a lot easier. So we enjoy cloud native security research. We've done some systems and software security, cyber deception, and of course, some security engineering and data science. So we're going to mix a little bit of each of that into today's talk. But today's talk's really about provenance tracking. So this idea of essentially being able to track through a set of processes and understand how data is moving through them, how control flow is moving through those, to be able to identify multi-step attacks. And we're going to do this through augmenting provenance graphs with security. And so we're going to talk really about data abstraction and look at this system provenance graphlet which really is a data structure that sort of compactly allows us to do provenance tracking. And then we're going to overlay or fuse in security labels on top of that, to be able to identify where there might be some integrity issues, and then show some security analysis on top of that. Fred, who I like to affectionately call the demogod, the demo god, is going to show some of that through a demo later on. But first, our first love is sort of runtime observability. And runtime observability, especially in a Linux system, can be really challenging because the collection of that is typically at the system call level. And so it's almost like trying to collect PCAP for a large network. It leads to a lot of sort of rule-based analytics. It's really difficult to store. It's really hard to analyze. And so our goal with all this work is really to be able to enable data science on top of system telemetry. And we do this in two ways. One is we focus on data abstractions and interpretability. So essentially raising up from this really granular system call level up into something that we can deal with, that we can provide context to, and so that we can do better analytics. And then around that, essentially providing sort of an open stack for system security and data science. And so going forth with sort of this multi-level data abstraction, I like to call this the straw. And so the idea of, as one of our colleagues always used to say, of sort of collecting telemetry, system telemetry, is taking a grapefruit and trying to shove it through a straw. And so to do this well, you can either try to increase the straw size or you can shrink the grapefruit. And what we're trying to do here is shrink the grapefruit. So if we look at the left-hand side of this, we get these sort of high-frequency system calls. And what we want to try to do is sort of create more of a behavioral abstraction from that, reduce it down. And we do this through creating sort of a relational or object relational data format, which we call SysFlow. We'll take a look at that quickly in a slide or two. So this allows us to sort of reduce the amount of system calls that we're looking at. And then we can take that and form it into what we call behavioral graphlets. And so as we move from left to right here, we're reducing the amount of data, but we're also increasing the amount of context and increasing the amount of state that we can do. And then once we do that, we can then do analytics, TTP tagging. We have a framework where you can sort of create all of these different analytic plugins that you like, so that you can do take your favorite AI algorithm, do security analysis, and it comes out a lot less noisy and a lot more sort of fully semantically useful out the right side. So just to give an overview of the architecture, on the left-hand side of this work, we have what we call the collector. And these all go into your Linux systems as agents. Our work is built on top of the Falco work, which is a library that essentially allows you to have a driver that can link into the kernel. And essentially through eBPF or kernel module or core eBPF, you can collect system call information and push that up into user space. And then we have what's called the collector, which can then take that raw data, converts it into sysflow data, and then we can stream it into what's called the sysflow processor, which is essentially an analytics pipeline, which lets you build different analytics. It has a policy engine inside of it. It has a graph engine, so we can build graphlets, and also we can build sort of custom plugins, to do graph embeddings, analysis, and things like that. Once the data gets shipped off that host, it can be done in several different ways. We have a whole sort of data science stack that can run on it, and Fred's will actually show some of that through some Jupyter notebooks. But we have different storage models where we can store it in S3, Elastic, or Druid. We have a data processing pipeline with different SDKs to be able to manipulate the data, do analysis, and things like Python and Go. Fred will show that as well. And then we have a Jupyter notebook, as I was mentioning. And all of this is again, to get a better understanding of the data, to be able to build analysis tools and go beyond rules, to be able to do some fun stuff with the data. So if you love data and just different things like that, this is a fun project. So I'll briefly go into the sysflow data format. For those that are familiar with NetFlow, it's one of the first big data sources that I worked with in my career. And it's really about sort of taking PCAP data or raw packet data and sort of merging them into session flows that can be then are a lot smaller and able to analyze. And so sysflow sort of takes sort of some of that in terms of its ideology. So it takes system calls, raw system calls, and then lifts that up into a behavioral sort of telemetry, which captures how a process interacts with its environment. So how it interacts with other processes, how it interacts with the file system, how it interacts with the network. And you can build essentially these graph-like structures from that. It's container aware, and it uses flow-centric analysis or semantics for system analytics, and we'll talk about that in a minute here. So here's just an example of what sysflow does and what it looks like. There's basically three types of objects in sysflow. There's entities, which are basically the particular objects that are going to either perform actions or have actions performed on them. So things like processes, files, containers, and Kubernetes pods. And so those are shown in green in this diagram. And then we also have events and flows. So events are things that are point-in-time happenings. So for an example, creating, cloning another process, executing another process, and they're separated out because of their importance in terms of time order. And also flows, which are also in purple here. We have things like network flows and file flows, which will establish sort of a session of an interaction with either another network end or a file end in terms of reading or writing to that. And all of those sort of system operations are combined and compressed into single records. And then as you can sort of see from here, you can start seeing sort of this graph-like structure that we can create, giving that context that's really important to be able to do security analytics and to identify exactly what's going on in your network. So the format, this is just a sort of an overview, similar to what I said in the last slide. We have process. A lot of this thing is very process-centric. And so for each thing, we have like an event and a flow. So we have a network event, a network flow, which would show you and certainly the hosts and things like that the process is interacting with. We have a process event, which would show you things like process cloning, process exiting, process execing, and a process flow, which sort of maintains the status of the process in terms of how many threads it has, running all of those types of things. And then we have essentially your file flow and your file events for deletes, unlinking, reads and writes and things like that. So there's a whole spec on this actually on the website, but this just to give you sort of an idea of the various types of objects that we have, and then we can, like I say, build this into graphs and do analytics on top of it. And this is an example of a sysflow trace using a tool called Sysprint. The idea here is that we have a server and a client, and the server and the client are interacting with each other. And each sort of row in the table shows a different sysflow record. Key points here is that it holds all of the information about, for example, a process. So things like PIDs, thread IDs, process name, things like that. It's object relational. So if we see this blowing up net flow, it has all the information about the net flow, and then it points into the process, which in turn points into a container if there is one. And so this helps us do compression. But essentially, one of the other key points here is the op flags, which is like, I guess, the fourth column. That shows the operations that are being performed in that particular record. And this can have one operation or multiple ones. So for example, in the first record, the server is execing. So it has that single exec operation. Whereas in the third record, that's actually a reading flow where it's reading the libc.so file. So we have an open, which is the O, a read, and then a close. And so you can create sort of using these operation flags, different events, and combine them in different ways. So from that, the sysflow graph, or sorry, the sysflow, we can then now create provenance graphlets. These aren't just sort of exploding graphs where each node is a single event or a single entity. What we're really trying to do here is create behavioral graphs whereby each node is sort of a coalescing of behaviors. So for example, in the graph on the right here, we have an HTTP server. For those that are familiar with Apache, typically you will have sort of a root process, which would be at the top, and it has a set of workers that it'll deploy and clone. And so instead of cloning nodes for each of them, we can actually coalesce them based off their behavior, and then essentially attach in the files that they're interacting with and the networks that they're interacting, the network objects that they're interacting with into a label-directed graph where events are labeled as edges that associate to process nodes to either another entity like a file or a network flow, or sorry, a network endpoint, and the like. And so then we can use these provenance graphs to essentially do root cause analysis, which Fred will show, and also talk about doing integrity on top of that. So I'll pass it over to Fred.
Hello, hello. I'm on? Yeah. So given all the background that Terrace has introduced about how we built those provenance graphs, now we talk about the main scope of this talk, which is how can we leverage security identifiers, the semantic of security labels that exist in the kernel, in the operating system, to allow us to go beyond low-level sort of rules for detecting security-relevant behaviors in Linux. So what we did here in this work that is in progress, we took our base to build those graphs, and we extended it with the collection of security labels from basically collecting the types from SLinux, and we augment our telemetry with that semantics. And the approach is very lightweight, as Tara was describing. There is no penalty really on the performance almost. We try to aim for portability, so that's why we chose to implement the prototype in eBPF. And in order to define what we call integrity walls or boundaries around the different process behaviors, we use the mandatory access control labels. There's one caveat here on this architecture that you see here. We need a way to translate the security identifiers, the SIDs, into the labels proper. And today, our current prototype leverage a cray probe on the security SID to context function. So this is something that we're going to table to the end of this talk. We're going to talk about potential, I guess, work that we could do, or perhaps extensions to the kernel that could make this more streamlined, so that we could collect this, do this translation directly when we are collecting the packets, the events into our eBPF driver. So right now, the way we do the translation, we create this hash table, this label map, that essentially we are hooking to the function when there are calls to this function, and we cache those labels. And then in user space, we read those labels. So that's the caveat here. So we have to have seen a call to that function, had to have seen an access to that file in order to have the label. So what we do a bootstrap on the kernel. So we do like a scan, we load this hash table, and then we do the mapping. So this is not our final solution. What we want to do, and we're going to talk in our last slide, is how we could actually make this in line with the collection of the packets with the system calls. So what we do here, at the end of the day, we extend those graphs with the semantics that we can carry with the types. So we're essentially collecting from SLinux the types of the binaries of the files, right? So for the files that we have in the file flows, we have the SLinux types. And also for the processes, we have also the type of the binary associated with those process nodes. There's something that we do around also collecting the entry points of the basic blocks and so on, but that's beyond the scope of this talk. The idea is that we want to associate with those types these concepts of high integrity, low integrity, this idea of potentially victim process, and this idea of objects that could potentially be controlled by adversaries. So basically, allowing us to rule detection in terms of first security principles, as opposed to knowing concrete values of a specific file or a specific process name. So to motivate this approach, we're going to look at this shell shock scenario, where we have this vulnerable Apache web server that is vulnerable. It's configured in a way in CGI mode and is vulnerable against the shell shock vulnerability. So an attacker can actually attack this server, write a file to the file system, for example. So it's a remote control execution vulnerability. And on the other hand, you have this cron job, and you have this slop admin that has written a com job that backups the server, so the contents. And here you see, for example, the SLinux label for the content type for this file that gets written to that folder, to that directory. So the slop admin has potentially written his rsync script in this way, and has also left, has left the dot here, the period in his path. So when it happens that when he launches this script inside in the context of this directory, instead of calling, the actual rsync of the operating system, is calling this a script that wraps rsync. and then it mounts the attack. So it's a multi-step attack, and there is an entry point that comes from the network that is affecting a process in here. So we'll see how this actually can be uncovered by means of collecting security identifiers and enriching them into the provenance graphs. By the way, the demo that I'm showing can be accessible here. So there's this link. There's also this QR code. It's in a Collab notebook. So anybody can go there and execute it. The traces, everything is in there. Also, the APIs that we extended from sysflow, the collector that we extended is also like all in open source in the branches that we have. We haven't yet made it to our upstream branches because we want to fix the issue with the RISC, how we collect, do the translation to the labels. But in a nutshell, yeah, if you go to that link that I sent and you click here, yeah, you should be able to execute this in your own environment in Collab. But I'm going to run here locally. So essentially, I'm going to be showing here what we did in terms of how we did the log hunting on top of the traces that we collected that has this security labels and all the system calls like Tara was talking about. So at the core of our approach here, we have this API. It's a graphlet that essentially can read from the data. So here you have the trace that we collect. So it's mounted in this data path. And this graphlet class, it's all documented in here. You can read later. Builds the provenance graph from the sysflow traces, because sysflow is a relational data format, right? So it has the linkages between the process objects, the process events, the flows, everything in there. So you build the graph as you read it. And we also have Go APIs for those graphs. So there's a way also to build them in string fashion. But I'm showing here is the Python API. And there is also a way for you to define policies, right, in declarative YAML format, where you can have like logical expressions on top of the sysflow attributes to match against different nodes, different places of the graph, and add tagging to it. So you can actually add additional semantics. So here you note that we have an integrity policy that we mapped from the mandatory access control labels or types. And we also have a TTP policies that I'm going to show at the end what it does. So we build a graph. And here I'm just printing the shape of this graph. So meaning this graph contains under this graph, we have 11,256 sysflow records. So that encompasses process events, file flows, net flows, all those things. And each of those records, they may have up to 79 attributes, right? So all the attributes that sysflow collects, so we flatten them. So, and if I visualize this graph, this provenance graph, it is a huge thing here, right? So it's actually beyond, it's a lot of nodes, and we can go on and on. But it's all the basically behaviors that we have seen during this collection period for the entire Linux host. There's no filters in here. So and it does coalesce things, right? So you have files coalesced related to this process. There are some processes that have lots of child that are coalesced together because they have the same behavior. But it's still, it's very large. The nice thing about sysflow, because it's all relational, you can take the data, maps to a data frame, and you can visualize in different ways. So this is another way to represent the entire host data. So here, for example, let's see if I can find. Yeah, there is Apache, for example, here. So if I click here, you have all the file flows associated with the Apache server. You have the actual process event. And we also have the network behavior. So you can see here that Apache is listening and talking to those IPs here and to those ports. So anyway, so sysflow is nice because it gives you a very easy way to look into what's going on in your system from a data science perspective. But you can also go deeper and see what actual records you have under the hood. So the same data I can filter, for example, for the Apache server that we just saw. And you can see the timestamps, the file flows, process events, the PIDs, the thread IDs, all the general attributes that we extracted from the system calls. And now, because we have the ability to get the SC Linux labels, we also have the process SC Linux label. So here you have the HTTP exact types, and also have the file types. So we're going to use that information to essentially define integrity rules to uncover multi-step attacks in this host without having to know where the attack was in the first hand. So that's the goal. So I'm going to skip over this because Tara will talk about this. And we define those very three very simple rules, right? Using SC Linux labels, like I said, the types of the binaries associated with the process and the types of the files. And basically, we are looking at the exec system calls and the open system calls, like the file system calls. We look at things that we deem to be low integrity. So for example, we look for sysflow. SF is the prefix for the sysflow record. File is the file object. SC label is the SC Linux label for that object. We look to pattern match on any list of what we call low integrity object identifiers. So those are the types. And in this case, could be any content type that is served by, for example, something that is network facing, Apache, FTP, and so on. For high integrity objects, we can think about anything that is more protected, that it shouldn't receive things from the internet or things that runs at higher privileges. So we look at processes that could potentially be victimized. And again, we look at the process, that's Linux labels, and we look at things like, for example, cronD and other processes that shouldn't be affected by low integrity objects. And here I have another rule that is tagging any nodes. Oh, and by the way, that's a tagging component that I forgot to mention. So when this expression matches, of course, we add this tag to the specific corresponding record and nodes of the graph. So here on the same token, I'm looking for any classes or types of processes that are, for example, network facing, right? And then I add like a label, vector, network. So with that in mind, let's go back to our example. I've already explained what it is, right? We have shell shock as our attack vector. Shell shock is indirectly affecting the execution of a higher privilege process, Chrome. There's a job in there, and it's hijacking Chrome to do something nefarious. For example, updating the sudoers file to give the Apache user, basically passwordless sudo privileges. So that's the attack. So the way you define this sort of security principle when you have this labeling system is that instead of saying, hey, let me see if I have a TTP or indicator of behavior for shell shock that somebody has extracted as a signature. No, we don't think this way anymore. Now we can think about, is there any flow for things that are deemed to be low integrity in this entire system that somehow finds a path in this provenance graph to something that in our integrity policy is deemed to be high integrity. And then what we do, we create those predicates, and we say, hey, graph, find a path that connects those two things. And lo and behold, what you get, it's something like this, that links, for example, cronD, the higher privilege process runs as root. It has the cronD types here, and links it all the way to the chain of execution. As you can see, there is the backup script that runs, and then it holds and calls that www.html binr sync was duped into calling it as opposed to the actual binr sync, all the way to going to that thing that was deemed to be low integrity, which is the rsync script here that is controlled by the attacker that was dumped through the shell shock attack to the file system. So here you have the direct, the indirect attack, right? A higher privilege process that is high integrity based on the type, cronT, that's being affected by the low integrity file, right? First security principle. And we could think about duals as well, like, for example, information leakage would be the opposite, right? And we can go further, right? Remember that we also denoted these classes of what? Vector-facing, network-facing classes of applications. So we can extend our predicate to say, hey, try to find any network-facing, because we are making assumption here, any network-facing application that could be linked to the existence of that file, of that var www rsync file. And lo and behold, you get Apache at the top here. Apache, launches its children. Those are the worker processes. So, the provenance graph that we have, remember, it coalesces things that have identical or semantically similar behavior. So you don't have like 4 nodes with 4 edges, like this ever-ending fan out. No, it actually coalesces. And then it goes all the way to the point where you have the injection, the payload here. You can actually see the payload that is hijacking shell shock. So there's a CGI process, the victim CCIG process, that is mapping to a vulnerable bash. It's duping that bash to execute via the GTP environment variables, basically hijacking that CGI process into execution bash. And then writing the file, you see the file flow? It's writing that rsync file to the file system. And see here, we have this little analysis that does the attack graph for you. So essentially, it's linking this file with the execution of the same file. So I like to think about this like as a dependently type sort of system. I mean, an analogy to it, where this exact after write is dependent upon the context, which is comprised by the graph, the provenance graph, and the types of the security identifiers, the labels. And because we can do this connection, then you have here on the other side, you have Chrome. And after this connection here, you know that everything else is tainted. And this is actually the behavior that we are seeing, right, where we are actually altering the sudo-rs file. So this is the entire kind of attack chain. It's a multi-step chain. It's disconnected, but because of the labels, we can bring everything together in a nicely way without having to do much hard coding, right, in terms of rules. So if you look past the state of the art in this, things like DARPA transparent computing, right? The entire work there was around like creating systems with provenance graphs where you have rules and patterns that have to be known a priori. You need to know the list of values, the list of process names. And in this case, you don't need anymore because you can leverage a labeling system that is already in the operating system. In this case, we did this in Red Hat 9.3. We also have rules for TTP tagging, right? Those can be false positive a lot. But in this case, we got four TTPs in here. One thing that I'm going to show you is that if I print from this graph here, this is G2, right? This graph that we uncovered attack. If I print all the nodes, you can see here the node where there is something odd going on. If I print the data in this node and just project on the executable and the environment variable of that executable, you see that this is in fact the bash. And bash is being injected with the HTTP user agent. If you remember shell shock, that was the attack, right, against a CGI-based web server. You would hijack this variable. You would prefix it with this string. And then after that, you were able to do whatever you wanted. It's a remote code execution vulnerability. So this is the end of the demo. But all of that was like, we were able to recover this attack for the entire, from just that, first security principle, looking for flows of control from the low integrity object to the high integrity objects that are mapped from the security identifiers. So with that being said, this gives us the policy, right, that we basically had in this demo, right? So we are looking for victim uses of these resources that an adversary can potentially modify. And in this work, we are actually working with our friends from PSU to come up with this sort of integrity policy, larger integrity policy based on SC Linux for Red Hat, where we have comprehensive lists of different types, if you will, that can be used for this kind of detections. So again, at system call, we want to basically apply these host graphs to annotate attack resources, and you want to be able to log to the detection based on that. So this kind of interactions that we have through files, types. One thing that we are exploring is the idea of leveraging extended attributes also to improve the semantics of the lineage. So certain tools like curl, they add extended attributes to files. So we could actually use those extended attributes for security purposes to know semantics of things. Oh, it's coming from a web browser or something like that. So that could also be helpful in our list definitions. And back to my point before, right? Right now we have this race problem where we are creating this hash table in eBPF to cache from a kprobe of the security SID to context function the labels so that we can do the mapping in user space. What we would like to do is potentially to declare or wrap this function as a kfunc so that we could potentially do the mapping directly in line as we're collecting the packages. So we don't know if this is the best approach, but this is one way that we think that could be easy for us to do this without incurring races or in this interaction where we have to cache things out of band. Could also have a user space API that we could call and do this mapping, maybe. But again, we'd like to hear from the community, hear from the experts, what could be the best approach. Of course, a eBPF helper would be even better, more stable interface, but I don't know what's the state of accepting new eBPF helpers by the kernel community. Yeah, and one word about compatibility, right? Why did we do this in Core E, eBPF? Because we wanted to achieve compatibility across multiple kernels, but sysflow also support legacy kernels, right? So we also have K-mods and things like that. So potentially, we could also implement this approach for legacy. Yeah, so this is the end of our talk. And I should probably acknowledge the US Army Research Lab. Part of this work was done when we were PIs in a grant. So, any questions?
Okay, this one's on. So it sounded like this is a source of many false positives and false negatives. So not sure when you would use this. Is the plan to grab some novel malware to understand it, to find where the problem is? Or what is the real goal with creating this?
So the real goal is to uncover, like I said, multi-step attacks, APTs, this kind of problems. And you're right that in general, all approaches that try to do that, they false positive a lot. And this included, if you're looking at like IOBs, indicator of behaviors, TTPs, they're prone to false positives, right? And so what we are trying to do here is to use an existing labeling system that a group of experts have defined already for the operating system, define those types, and then define those security principles, right, that could label potential paths that could be associated with something potentially malicious. So again, false positives. But the idea is for log hunting, right? You saw what I showed before, like when I said, I showed the tree map, like 11,000 nodes and things like that. So someone who is in the business of doing threat hunting and is dealing with this large amount of data, it's like very large amount of data. In sysflow, we have 11,000 records. System call-wise, that would be probably 2-3 times more, if not more. So when you're sifting through these logs, say audit logs and things like that, how do you know? How can you make sense of this more semantic behavior? So we're trying to add levels of semantic. And even if you have false positives, for someone who is doing the log hunting, this, I think, it's easier for you to, separate the good from the bad than look at the, the very granular, data that you would have. And also, we are tagging things on a much higher level, coalesced. So you only have one of those flows as opposed to have thousands of the same things happen for every system call that has the same behavior. So that's much more verbose. Like tagging on specific system calls is much more verbose than tagging on like those large provenance graphs. Does that make sense? So even though it may false positive, the number of those false positives would be much smaller. So,
just to add to that, one of the big areas of research right now is looking at how can we take these large provenance graphs and start the items that we identify within them, link them up into the kill chain to different phases of the kill chain. And so the idea there is if you start getting more dots on that kill chain, then you're more likely to have found something that is malicious. And so the idea here is to be able to bring that together for the security analyst.
Yeah.
Thank you.
Yeah.
In the file flow stuff, I noticed you had, you're tracking open, read, write, et cetera, as well as bytes written
Yeah,
that stuff.
we have a bitmap.
Yeah. Are you actually tracking like bytes being passed through read and write?
So we have volumetric counts on the number of bytes written, read, the number of system call operations, write system call operations, read system call operations.
Okay.
So we have an entire bitmap and also the open flags.
Do you have any way of tracking like some file operations are going to do their read and write through the virtual memory system, like via mmap?
Yeah, we do.
Are those just
yes,
invisible?
yeah. We could track the mmap calls.
Yeah, mmap are tracks as
So you
well.
know the mmap happens, but not necessarily how much data was read.
So yeah. Okay. Yeah, exactly.
Just wondering if you had a magic wand that you've used for that
No,
or not.
no.
Okay, cool.
No.
In the demo here, you talk a lot about basically detecting privilege boundary crossing events. More recent events have showed us we are looking also now at behavioral analysis of, say, a build system that's building, I don't know, XZ. What sorts of processes are writing to what sorts of files?
Right.
Have you tried any kind of analysis yet of that?
Not yet.
Okay.
So well, actually, we have for the CI/CD pipeline.
Yeah, go ahead.
For and so you can find some
Don't
pretty
say
interesting.
word. Don't say word.
Yeah. So you're able to find things like people having like open passwords and all of these types of things, and really be able to trace back where some of those issues are in terms of misconfigurations and all that kind of stuff.
It was some accidental findings in CI/CD pipelines for cloud. So, but we never did on purpose for supply chains in general. That was a very interesting thought.
Thanks.
Hi. I like this approach. I was wondering, how do you store all the execution flow and valuable information, the graph? How do you store it? How do you extract it from the kernel? Do you compress it on the fly? Or do you just expose a map to user space? And which format do you use?
I didn't quite hear it.
He's talking about how we build it, how we store it, where do we store it?
So basically what we do is we can each node is sort of a coalescing of a bunch of records that are underneath it, and so we can actually decide how much granularity we want to store per node based off of what kind of storage we have. So we like to use a lot of S3 because S3 tends to be really, really cheap, so you can actually save more. So we'll use like databases like ClickHouse or Drill, which can allow you to push back to an S3 as a backend store, and then essentially we for storage. We're using those sort of column-oriented databases, and essentially we can have sort of a higher level representation node, and then have sort of subnodes that are sort of mapped to that particular node, and we can rebuild the graphs from that.
And we have used Avro as the
front. We use a lot of Avro.
Binary serialization through Avro as well for the storage. So there is in the Syslop, the GitHub project. If you're interested, you can.
We're happy to talk. Happy to talk about it.
We can show you
more,
where things are.
But ClickHouse has some nice features where you can actually build for like subtables within a row. So you can have like little sort of mini subtables. And so essentially think about each row being a little table. And so we can create it where a row in ClickHouse is essentially all of the sub rows that make up that node that we coalesce in the picture in the presentation.
Okay. And what is did you measure the performance impact of recording all these events?
Yeah, the performance impact of recording all the events.
Yes. So everything is done passively, and we do recording-wise. We do all that offline. I forget exactly what the percentage points is. I think it's a few, anywhere from. It depends on the workload.
Yeah. It's negligible on the processes. So if you have a large enough machine, I mean, large enough is not a big machine, like, more than one processor, it's not going to be an effect on the processes that are running the machine, right? So the collector itself takes up to one virtual CPU, for example, one node. And it's all done in stream fashion. And the way we serialize it in Avro, and then we have a couple of ways of sending the data out. We have a stream exporter, and we also have a batch exporter that puts into S3. So depending on the mode you deploy this system, you're going to have options on how you're going to bring the data out. Yeah. But essentially, no, it's not a big footprint in the machine. Maybe a couple hundred megabytes of memory footprint, and then up to one virtual CPU.
Yeah, we tend to. So we had one cloud installation where we actually mounted S3 as a little drive that we mounted, and they wanted the people we were working with wanted to be able to store the raw sysflow files in there, and so we just actually in 5-minute intervals would drop the sysflow files in there, and it would get written directly to S3. So that was a way to do that. Yeah.
Last question: do you intend to? Are you only interested by SNX, or did you try to use other informations like basic one like QAD, GID, and so on, or either second filters, eBPF programs, Nanox sandboxes, stuff like that?
Yeah, so I would say we're always trying to find interesting indicators of things. So for example, even knowing in a Kubernetes deployment that the file is getting read off, a Kubernetes Docker container will use a layered file system. So knowing that you've gotten the file off of the top layer tells you a lot, for example. Other things that we were talking about, Mimi over here, we have been talking for a long time about incorporating things like IMA, so being able to do the hashes and things like that. So a lot of these semantic, indicators that sort of, provide more information about those things. We're always looking for those types of semantic labels and things that can make this better. Because the whole idea here is to be able to sort of filter out that noise and really understand exactly what the program is doing. And so the more type of information that we can use for that, I find it's really useful.
Yeah, there's always a trade-off, but yeah.
Thank you.
All right. Okay, so that concludes our talk. Thank you for listening.
Thank you.
abstraction layer within the Google agent, or at least an agent that is speaking standard protocols. And
hello? Hello? It works? Yes. Okay. Okay, so
okay, good. Oh, it's expired, or there's a new one. Okay, what's that measurement? I'm going to make sure that I upgrade to that after I go and change my policies. There is already a package in Ubuntu that says I need to upgrade my firmware. Here's the firmware, and it will go and change the TPM policies for you, and then go and yeah, it reseals, and then it will use the firmware maintenance protocol, which will be on to go and install the new firmware. Right. So we need to have that protocol.
hello? Hello?
Oh, there's ice cream over there if you want it. They first brought it out there, and we grabbed some, and then they wheeled it off, and we thought, oh, there's somebody else.
Okay.
We're not allowed to.
Yeah. Hello, everyone. Good afternoon. My name is Roberto Sasso, and I'm from Huawei, from the Terrace Research Center. And today we present the Digest Cache LSM, which is software for integrity, and we aim to bring to the masses, to everyone. So first, I'm a kernel developer since 2006, and I have a background in trusted computing and security. And I recently became IAMA and EVM co-maintainer. So first I will give an introduction. I will state the problem, and I will talk about the solution, Digest Cache LSM, and I will draw the conclusion. When we talk about integrity in the Linux kernel, we talk about integrity measurement architecture, which has two main functionality, measurement and appraisal. So for measurement, IAMA is able to intercept file operation and record the operation in kernel measurement list, and protect the integrity of this measurement list with a cryptographic chip called Trusted Platform Module. And for appraisal, recording the digest is not enough, so we need the file signature to verify the file provenance. And IAMA basically verified the signature of the application of the file with keys that are embedded in the kernel. And if the signature verification succeeds, grant access to the file, otherwise denies it. So the first problem that prevents integrity to reach the masses is that the TPM is low. And when we compare the time for measuring bin cat, without the TPM, the operation takes 640 microseconds. And if we see the time with physical TPM, it raises to 7,000 microseconds. So it's a huge increase in the overhead. And for the emulated TPM, the time is 1,900 microseconds, which is much better, but this is because the emulated TPM runs in software. So the second problem is that if we want to seal a key to the integrity PCR, the TPM register, we have a problem because the way the system boot changes every time. So we boot the system, we found that the TPM key can be unsealed, can be usable, but we reboot the system and suddenly the TPM key becomes unusable. And the reason is that if we compare the order in which a service started, we see, for example, that the avoid daemon in the first boot is the second entry, and it became the fourth entry in the second boot. And if we look at the ASA state, is the second last entry in the first boot, and is the second in the second boot. And why this is a problem? It is a problem because the PCR extend, so the operation to protect the integrity of the measurement list, depends on the current register value. So we send a new measurement for extending the PCR, and we concatenate with the current value, we do hashing, and we obtain the new PCR value. And this new PCR value is used as a current value for the new measurement. So here in the bottom, for example, we can compare two measurement lists. The first, I measured the file ABC. and I obtain a PCR value, and if I measure instead BAC, I obtain a different PCR value, and which means that the TPM key is not usable. Third problem is that, so normally the RPM package has all the information to verify a file provenance. So it contains the file digest, which are signed with a PGP signature. But IMA does not understand this format. So it has to add a new section in the RPM header called the file signature, which contains the signature in the format that IMA understands. But the problem is that this is redundant. There are more signatures to verify, and also increase the size of the header. However, this solution has already been accepted in Fedora and 39 and Red Hat Enterprise 9. Okay, so IMA managed to add the file signature to our RPM, but what about the other package format? So do we need to modify also? So we need also to modify those to implement to add the IMA signature. And so the generic problem is that, so we, in the world of software vendor, the software vendor already provided the checksum information in their format. And the access control mechanism, so the integrity provider cannot use this information because they don't understand this format. So how we can bring these two worlds together? And the answer is the solution that I developed called Digest Cache LSM, which currently supports the RPM format and a type length value based format. So how the Digest Cache LSM fits in the picture? So the integrity provider, IMA, IPE, or BPF LSM, want to know if a file that has been accessed belongs to a distribution, comes from a package. So they do a query of the digest to the file digest to the Digest Cache LSM. The Digest Cache LSM is able to read this data source, the packages, which are measured by IMIP or BPF LSM themselves. And then the Digest Cache LSM extracts the digest from the packages and is able to perform the query and to tell to IMA if the file comes from the distribution. So now we talk specifically about the changes, the integration of IMA with the Digest Cache LSM. So conditions for using the Digest Cache LSM are that the query result is positive, so the file is found, the digest is found. We measure the package, the digest list, and we allow the usage of the Digest Cache LSM with the IMA policy. If all these three conditions are met, then the action is to skip the measurement. So we want to solve the problem of the TPM being slow, then we cut measurements. And for appraisal, we say appraisal is successful. And if any of the condition above is false, otherwise we still do the measurement. And for appraisal, we fall back to other methods, like, for example, verifying the extended attribute, the file signature. Okay, so now we are ready to find the difference between the original style of the measurement list and the new style of the measurement list. So on the top, this is the original measurement list, where we have some file and their digest, and some file they even have a file signature. So we send this measurement list to the remote verifier. And what the remote verifier does is to do a digest lookup in a reference database that the remote verifier built from the RPMs, or verify the signature of the file with a key that the remote verifier trusts. And in the bottom, the situation is much different. So we don't have the file digest anymore. So we have the measurement of the package with the signature. And we have the measurement of the file was digest is not found in the package, just those. And during the remote attestation, we do the signature verification for the package, of course. And now the key point is that, so we don't have the measurement of the file anymore. So the remote verifier guesses from the measurement of the package that a subset or all the file from this package could have been accessed, but the remote verifier does not know which file have been accessed and in which order. So there is a loss of information. So this is a loss in order to gain more performance because we use the TPM less. And we will see this in a few slides. And the second point is that we find an unknown file. And so while the first measurement, the original measurement list does not tell anything about if it is the verification is successful or not, The second, if there is an unknown file, already means that this file does not come in, from the distribution, and then the attestation fails. And for appraisal, we can see the difference of the software manufacturer between the original style and the new style. So in the original style, IMA requires infrastructure modification to sign the file individually and to add this signature to the package. So the package then is created, is signed, and during the deployment, there is an RPM plugin which extracts the file signature, add them to the files, and IMA appraises the file signature. But with the new style, so with the Digest Cache LSM, we don't require any infrastructure modification. So we build the package as we do today. And even if we take a package from 2000, this should still work. And when we deploy this solution, we do appraisal of the RPM header because we have the PGP signature. And the Digest Cache LSM also extract the digest from the package, and the IMA do the lookup of the digest. And here we see that the other difference is that we do only one signature verification for many files, for all the files that are in the package, versus doing a signature verification for every file. So now the question is why I developed an LSM, and so we can compare the old architecture called IMA Digest List that I presented a few years ago, and the new architecture. So in the old architecture, basically there is a need to explicitly load all the packages to the kernel memory, and we create a huge database, and IMA is doing a query on this huge database. But with the LSM facility, we have a possibility to attach information in the inode security blob. And that means that we can attach the database, so the digest extracted from the package directly, and we link to the inode security blob. So the LSM infrastructure and the virtual file system act as an indexing mechanism, so I don't need to implement myself. And the second point is that we do loading on demand only when IMA requires to appraise one file. Then we just load the relevant package. And finally, the LSM infrastructure gives notification to the LSM when there was a free, so the inode is evicted from memory, so we can free the database also for the digest. And where there is a write on the package so that we invalidate eventually integrity verification results. So now we are ready to talk about the information that are added to the digest cache, which is the main object of the digest cache LSM. And the first information is a set of hash tables, which contain the digest extracted from the packages. There is one hash table per algorithm. And the second information is the full path from which the digests were extracted. And there is a reference count which tells how many pointers of the digest cache are given to the other kernel components. There is the verification result of the package. So when we verify the PGP signature of the package, here we have the result. Then there are the nodes which are using the digest cache. So when IMA needs to do appraisal for a file, we have here the list of the node for which the digest cache was requested. We can also create a digest cache for a directory. In this case, since we don't have a regular file, we don't have the hash table, they are empty. And instead, we have a list of directory entries, which are the digest list, the RPM packages. And now, as I mentioned before, we can reach this object, this digest cache, from different locations. So if we are in the inode security blob of the digest list, the RPM package, the pointer in the inode security blob is called dig owner. And we have also mutex to serialize the check and the assignment of this pointer. If we access the digest cache from the node when we do appraisal or measurement, this pointer is called a dig user, and there is also a mutex to protect the check and the assignment. And now we can look at the API of the digest cache LSM exposed to the integrity provider, so to IMA, IPE, and the BVF LSM. So the most common API that we want to use to, for example, to query for a digest is the user API, and it includes digest cache get, digest cache lookup, and the digest cache put. And there is another API called the Integrity API, which is used for annotating the result of the verification of the signature of the package, and to decide if we want to use the digest cache. So if the PGP signature verification failed, for example, we don't want the digest cache to be used because it was created not from authentic data. And lastly, so we have a digest list parser to parse the different data format, and we have the digest cache htable init, add, and lookup, which are used to initiate the htable, to add the digest to the htable, and to do a lookup. So IAMA is doing now an appraisal or measurement of a file and needs to call digest cache get first as part of the query. So the digest cache LSM now determines the digest list location. So from where, from which file the digest should be taken, and it can be a predefined file or directory which is set in the kernel configuration. Can be also changed at runtime, or we can have a combination of a predefined directory or and the file name in this directory is included in an extended attribute of the file for which the digest cache should be used. For example, if we have bin cat, it contains an extended attribute with value RPM coyotes, which is the name of the package which contains the digest also of bin cat. So we now create an empty digest cache. And the digest cache LSM read the digest list, and this trigger a measurement from IAMA, IPE, or BPF LSM, which annotated the verification result of the digest list into the digest cache. Then the digest list parser extract the digest from the digest list and add them to the hash table. Now the lookup. So in the lookup, we have two possibilities. Or we obtained a digest cache from a regular file, so it contains all the hash table, and we can do the query directly. Or we obtain a direct directory digest cache, which contains a link of the digest cache for each directory entry. And why we need the directory digest cache? Because, for example, in the initial run disk, we don't have extended attribute, so we need a way to do a query even if we don't know the precise location of the digest list. So then we can do the query of the digest, and the digest cache LSM returns a pointer to the digest cache, and we can call this function digest cache verifget, which is the function to know if the PGP verification, signature verification succeeded or not. Because if it didn't succeeded, then we discard the digest cache. We cannot use it. It is unsafe. And finally, we release the digest cache when we are done with a query. Or, as I said before, with LSM infrastructure, notifies when there is a node is evicted from memory. And the digest cache LSM just release a reference to the digest cache. And when the reference count is 0, the digest cache is freed completely. So we don't need to create the digest cache every time we do a query. So there is a caching mechanism. And so the digest cache pointer can be stored in the node security blob. And if it is stored, then we just return this pointer to IAMA. Or so if we don't find in bin cat, for example, this pointer, and we have to do the lookup in the digest list, so in RPM coyotes. And again, we go to the node security blob, and we check, in this case, the dig on pointer. And if there is a pointer, we return it to IAMA and IPE or BPF LSM. And in the worst case, we have to create the digest cache. So the final part is that we can have some changes in the file system. And for example, we can do set remove xatr, which change the link between bin cat and its relative digest list. And in this case, or when, for example, there is a write to the digest list, we have to invalidate the digest cache that we created before. So we set a reset bit. And when we set a reset bit, basically, we don't return this pointer that were stored in the node security blob. And we do what is called a reset. So we release the pointer, and we create a new digest cache from scratch. And the last part, so there is a reset. IAMA is not yet aware about it, but IAMA verified some file with the digest cache. So what we do is basically to send a notification to IMA with a pointer of the digest cache and the node, and we say to, and IMA basically says, okay, the integrity verification that we did before is not valid anymore, so we need to do again a query with the digest cache. So I mentioned that the second problem is that we need to have predictable measurements in order to do the TPM key sealing and unsealing. And did we solve the problem with the digest cache LSM? So if we see the measurement list on the left, so I included a file from the same package. And the resulting new style of the measurement list on the right just contained the measurement of the package RPM coyotes. So in this case, it seems it works. But when instead we also combine a file from two packages, so in this case we have in the first measurement list cat, date, and LVM. So LVM is from a different package. So LVM is the last in this case, but if you see in the third measurement list in the left is the first. And this causes the measurement of the package to be swapped. So actually, again, we obtain a different PCR value, and this means that the TPM key cannot be used. So we need an additional mechanism to fight this issue, and it's called the prefetching mechanism. So I said before that the digest cache LSM needs to determine from which digest list, or from which file it extracts the digest. But instead of asking the VFS to do a file lookup, what we do is to say, OK, we check the directory, and we scan the directory entries in a specific order, always in a deterministic order, until we find the file that we need. So in this case, we need, so I'm asked for wants to do a query of bin cat. And RPM coyotes, you see, is the second file. But when we do the scan of the directory entries, we trigger a measurement. So in this case, we first trigger the measurement of RPM LVM2, and then RPM coyotes. There is a prefix, which is a sequence number, which is to define the ordering of the directory entries in the directory. And if we accessed, for example, LVM, it will be the same, because since we scan the list in the same way, the measurement list will always contain LVM2 first and then coyotes. And the other problem is that, OK, so now the PCR is predictable because we obtain always the same measurement list. The problem is that the list changes every time we include a new package, because so we extended the PCR for every measurement entry. And in this case, so the sealing policy of the TPM key should be an OR, where we include a value for each entry of the measurement list. And so so all these combinations should be allowed. So now we see the performance. So if with the digest cache LSM we obtain a performance improvement, and I did a test with Fedora 38 with 4 CPU and 16 GB of RAM. And to obtain a predictable result, I pinned the QEMU process to physical cores, and I set the priority to -20. So the test consists in creating 20,000 files, and we add them randomly to 303 measurement digest list. And why we have this number? Because I checked the ratio of all files installed in the system and the number of packages. So I divided the number of files per packages, which means that every package contains an average of 66 files. So this is why this number. To compare with IMA appraisal, the original appraisal, I added also IMA signature, CDSA P384. Same as Fedora 38, 39. And I created an access list randomly. So there is a list of files that will be accessed sequentially and in parallel. And I checked, so basically we are reading this file and checking the time that is required to read all these files. So the test is repeated 5 times, and I took the average value. So we can see on the left that basically if we don't have the TPM, the measurement the time is pretty much the same. But when we switch to physical TPM, we see a huge delay for the standard IMA. But since with the digest cache LSM, we don't measure all the files, but we just measure the packages. So with standard IMA, we do 12,313 measurement, but the IMA and the digest cache LSM, we only do 303 measurements, so much less. And this means that practically there is no overhead compared to not using the TPM with the digest cache LSM. And yeah, the situation is better with the emulated TPM because the emulated TPM is faster. And even if we go from sequential access to parallel access, we see that the situation is pretty much the same. So the most surprising result is for appraisal. So in this case, the TPM is not involved, but we are verifying the signature of 12,312 files. And compared to verifying the signature of 303 files, we see the huge difference. So in IMA appraisal, the normal IMA appraisal takes around 100 seconds. And the IMA with the digest cache LSM, so just with appraisal of the package, just take, I think, 34, 35 seconds. And the situation is a bit better when we switch from sequential access to parallel access, but still there is difference between standard IMA and with the digest cache LSM. Memory occupation, because we have a huge measurement list with the standard IMA with 12,313 measurements. Standard IMA, of course, occupies more memory, and the digest cache LSM less. But with appraisal, IMA does not keep in memory anything, so that's why standard IMA takes less memory than the digest cache LSM, because the digest cache LSM has in memory the digest of the packages. So in conclusion, the digest cache LSM is a generic component for use by the integrity provider, and can be IMA, IPE, or BPF LSM. And there is a huge performance improvement compared to standard IMA. And it does not require any change for Linux distribution to adopt this solution. And if we want the lowest overhead for integrity measurement, then we can switch to FS-Verity. But in this case, the RPM headers do not contain the FS-Verity digest. So I wanted to propose to include this information in the new package. And that we have the links. So I recently sent the version 4 of the digest cache LSM patch set and the V2 of the IMA integration, and there is a user space tool to create the package in a format that digest cache LSM understand. And I also created the binary package for open source Tumbleweed, and it's possible to try, and I welcome any comment and suggestion. Thank you very much.
Okay. This is not a question, just I don't know if everyone noticed that in the graphs about the memory consumption, the vertical axis does not start at 0.
Okay.
Yeah, so the difference is not that big as it may.
Yeah.
But
you're right.
I mean, if we had the full scale, then the difference would not be visible. So I understand it just.
Yes, the way it was created.
We should always warn when something like that is shown in a graph, because many people just assume it starts at 0.
Yeah. Good point. Thank you.
This looks a lot like what Chris Fenner is trying to do for EFI drivers in the TCG, called the measured boot manifest. It's a very similar concept. But what's missing here in comparison to that is a second measurement showing that you have gotten everything that you expected, versus or another event that you measure, which would be that you got something that violated expectations.
Yes. Yeah, so this is the big difference. So in the normal measurement list, you have a list of files, and this list does not tell anything about the expected state. But in the second case, you have a measurement list, and you have the expected state, which is all the files come from a package. And if there is a deviation from this state, then you see immediately this unknown file. And that's exactly the measurement that revoke the TPM key, because the PCR is updated. And then the TPM key that is seeded to the correct state is not usable anymore. So this is really the fundamental building block for implicit remote attestation, where you have a TPM key, for example, for a TLS communication. And this TLS key works only if you access only a file from the distribution. And as soon as you access something that is different, then the TPM key is unusable, which means from the other side that, okay, there is something going on because I'm sending a challenge and the other system is not able to reply to this challenge. And this is the way to do, another way to do attestation based on the ability to reply to the handshake.
There's also the open-endedness that you have for the collection of packages that seems like you would need to have a signed bill of material for what's an allowable collection.
Yes, yes. So we can support a different format, and the easiest way, the easiest format to support is the RPM, because there is the file digest, and this part is signed by a PGP key. So what I also need in my solution is to support PGP keys and signature in the kernel, because I need to embed the PGP key from the distribution in the kernel to do signature verification. But for example, for Debian is a bit harder because Debian has a different way to provide the checksum. So currently, as far as I remember, there is an MD5 sum, but this is not signed directly. It's signed through indirection. So there is a release file which is signed, and then this release file contains the digest of other files and two other files. So we need to do a sort of a nested verification, which we don't support now, but I already designed the digest cache LSM with that in mind.
There are economic pressures to make distributions use different formats. The Internet Engineering Task Force is working on standardizing new formats like CORIM for giving reference integrity manifests that would give you more provenance information than what you get here.
Yes, and in this case, so the digest cache LSM is extensible, so you can develop a new parser, and this new parser supports the new TCG format, and from the digest cache LSM perspective, it's just a way to extract digest, but then the data structure will be the same.
Okay, thank you.
Thank you. Any other question? No? Then thank you.
Like an excellent idea. You know. Ice cream bar, you know? Yeah. I'll start with the ice cream. We have ice cream here. The night will evolve.
Whenever you don't start at zero, just make it prominent. It's okay. I just pretend that he didn't say it. Yeah. Okay, yeah, that's a good one. Yeah.